reputation rests on his Almagest, which may be regarded as the astronomical gospel of the Middle Ages. Hipparchus, as we have seen, found the current representations of the planetary motions inaccurate and collected a number of new observations. These, with fresh observations of his own, Ptolemy employed in order to construct an improved planetary system. Following the idea of Hipparchus, Ptolemy thought that the Sun and Moon moved in circular orbits around the Earth as a center. Ptolemy's chief work was to expand the system of epicycles so that it could explain discrepancies between theory and observation, discrepancies overlooked or ignored by Hipparchus. The deviations of the planets from the ecliptic, for example, were accounted for by tilting up the planes of the epicycles. Thus, with the aid of the system of Hipparchus, supplemented with his own idea of tilting epicycles, he worked out with great care and labor the motions of the planets. Although the Hipparchian Ptolemaic doctrine was framed on an extravagant estimate of the importance of the Earth in the scheme of the heavens, yet it must be admitted that the apparent movements of the celestial bodies were thus accounted for with considerable accuracy. For 14 centuries, the Almagest was regarded as the final authority on all questions of astronomy, and it may be considered as the loftiest piece of calculation appertaining to the ancient world. End of section 8.
Section 9 of the Science History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Edward Labonte. The Science History of the Universe, Volume 1, edited by Francis Rolt Wheeler, Astronomy, Chapter 8, The Solar System, Modern Investigation, Part 1. The Ptolemaic system of astronomy was discredited only at an epoch nearly simultaneous with that of the discovery of the New World by Columbus. The true arrangement of the solar system was then expounded by Nicholas Copernicus, 1473 to 1543, in the great work De Revolutionibus, to which he devoted his life. The first principle established by these labors showed the diurnal movement of the heavens to be due to the rotation of the earth on its axis. Copernicus pointed out the fundamental difference between real motions and apparent motions. He proved that the appearances presented in the daily rising and setting of the sun and the stars could be accounted for by the supposition that the earth rotated just as satisfactorily as by the more cumbrous supposition of Hipparchus and Ptolemy. He showed, moreover, that if the ancient supposition were true, the stars must have an almost infinite velocity, and declared that the rotation of the entire universe around the earth was clearly preposterous. The second great principle, which has conferred immortal glory on Copernicus, assigned to the earth its true position in the universe. Copernicus transferred the center about which all the planets revolve from the earth to the sun, and he established the somewhat crushing truth that the earth is merely a planet pursuing a track between the paths of Venus and of Mars, and subordinated, like all the other planets, to the supreme sway of the sun. This great revolution swept from astronomy those distorted views of the earth's importance which arose, perhaps not unnaturally, from the fact that the observers chanced to live on this particular planet. Whether the actual services rendered by Copernicus are commensurate with his fame may be doubted. He labored under the weight of an ecclesiastical tradition that could not be abandoned without some risk. He was a bold man indeed, who dared to overthrow or even to question orthodoxy and to diminish the Earth's overshadowing importance in the solar system. The Copernican system was not flawless either in theory or logic, and many objections could be made to it. Particularly by an astronomer who had observed and studied the movements of the heavenly bodies. After the example of the ancients, Copernicus assumed as an axiom the uniform circular motion of the planets, and as the only motions which are observed are in a state of incessant variation, he was obliged, in order to explain the inequalities, to suppose a different center for each of the orbits. The Sun was placed within the orbit of each of the planets, but not in the center of any of them. In other words, he still adhered to a system of epicycles. Consequently, the Sun performed no other office than to distribute light and heat. Excluded from any influence on the system, the Sun became a stranger to all the motions. The fixed stars were alleged to be stationary, and it was necessary to suppose that they were almost infinitely distant, inasmuch as they always seemed to preserve the same position when viewed from the opposite sides of the Earth's orbit. While various astronomers showed some disposition to accept the Copernican teaching, most of them were bitterly opposed to it on ecclesiastical, traditionary, and scientific grounds. Tycho Brahe, 1546 to 1601, was the most distinguished of these opponents. Being an indefatigable observer and practically the first to realize the value of continuous observation, he enriched astronomy by a star catalogue and studies of the movements of the other heavenly bodies. Tycho accepted the Copernican conception of a central sun, but rejected the idea that the Earth moved. Thus, he sought to effect a compromise between the Ptolemaic and Copernican systems. It was the study of a comet in 1577 that led Tycho to formulate his ideas of the solar system. He believed that the comet X, as shown in the accompanying diagram, was revolving around the Sun at a distance greater than that of Venus, and assumed that both the Sun, C, and the Earth, A, were centers of revolving systems, the 5 planets revolving around the Sun, and the entire system in turn moving around the Earth. This incorrect proposition, which was one of the least of Tycho Brahe's contributions to astronomical science, is significant, showing as it does how difficult it was for the principles of Copernicus firmly to establish themselves and planetary motion to be explained satisfactorily. Whatever Tycho may have thought of the Copernican system, his contemporary Galileo, 1564 to 1642, was willing to accept it. It has been shown how Galileo, with the telescope of his invention, was able to extend astronomical science and to introduce new methods of observation, which came naturally to one who was a leader in the experimental science of his time. But even before his work with the telescope, Galileo had adopted the astronomical views of Copernicus and collected arguments for their support. He was able in 1604 to confirm the discovery of Tycho Brahe that changes take place in the heavens beyond the planets, and that there was an important region beyond the Earth and its immediate surroundings. As was but natural, the use of the telescope broadened Galileo's horizon, and true scientist that he was, he immediately brought to bear his new discoveries on the fundamental conceptions. Thus, his discovery of the satellites revolving around Jupiter as the planets themselves revolved around the Sun not only rendered necessary the explanation of these new bodies, but dealt a serious blow to the infallibility of Aristotle and Ptolemy, neither of whom had any idea of the existence of these satellites. Further support was given to the Copernican theory by the ocular demonstration of these satellites revolving around Jupiter and not dropping behind, just as the Moon was required to move around the Earth, a mechanical difficulty brought forward by the opponents of the Copernican idea. As Galileo developed his astronomical ideas and discoveries, he naturally came into conflict with ecclesiastical authority, and there began the unfortunate controversy as to the relative validity in scientific matters of observation and reasoning on the one hand, and the authority of the Church and Bible on the other. Controversies such as this were conspicuous in the latter part of Galileo's life. They culminated in his famous trial and formal abjuration of his alleged errors, and in his conviction, quote, of believing and holding the doctrines false and contrary to the holy and divine scriptures that the sun is the center of the world, and that it does not move from east to west, and that the earth does move and is not the center of the world. Also that an opinion can be held and supported as probable after it has been declared and decreed contrary to holy scriptures," unquote. Despite Galileo's abjuration, his general attitude toward the Church and Bible is contained in his approval of the saying of Cardinal Baronius, quote, "that the intention of the Holy Ghost is to teach us not how the heavens go, but how to go to heaven," unquote. His attempts to explain and demonstrate the Copernican system in his great astronomical treatise, Dialogue on the Two Chief Systems of the World, the Ptolemaic and Copernican, led to his trial and conviction before the Inquisition. Kepler, another of Galileo's contemporaries, did more even than the great Italian to bring about a proper conception of the solar system and the motions of the planets. A student under Tycho, it was but natural that Kepler should have imbibed from his master a respect for systematic observation, regardless of the correctness or incorrectness of Copernican views. As a result, Kepler early adopted the Copernican doctrine, opposed though it was by his master. His observations led him to the conclusion, however, that even Copernicus had not revealed all the mysteries of planetary motion, and that the hypothetical circles in which the planets revolved around the sun, according to Copernicus, did not agree with the paths observed. Under the instruction of Tycho, Kepler addressed himself to the problems involved in the planet Mars, whose positions as seen in the sky were a combined result of its own motion and that of the Earth, as both move around the sun. Actual observation of the planet and the consideration of various geometrical theories that suggested themselves eventually led to the conception that the path of the planet must be some form of an oval. Finally, Kepler reached the conclusion that instead of being circular, the planet's motion must lie in the simple curve known as an ellipse, and formed by taking an oblique section of a cone. While the circle has but a single center, the ellipse depends for its form upon two fixed points, each of which is termed a focus. It can be drawn by using two pins stuck in a sheet of paper and by inserting a pencil within a loop of string that also includes the two pins. The curve may be traced by moving the pencil while the string is kept taut. It will be found that if the 2 points are kept close together, the curve approaches in form a circle, while if they are separated, the figure becomes elongated and possesses what the mathematicians term greater eccentricity. At any rate, every point on the curve is such that the sum of its distance from the two foci is always the same. Kepler found that the sun was at one focus. When the planet was near that focus, it moved with greater velocity than when at the opposite part of its orbit. The speed of motion, however, was always proportional to the area swept out by a straight line from the sun in equal intervals of time. In other words, there were formulated the now famous first and second laws of Kepler as follows. 1. The planet describes an ellipse, the sun being in one focus. 2. The straight line joining the planet to the sun sweeps out equal areas in any two equal intervals of time. Kepler not only established these laws for Mars, but immediately applied his principle to Earth, and then claimed, without proof however, in his epitome of the Copernican astronomy, that these two fundamental laws applied also to all the planets and to the motions of the moon. Accompanying these two laws was the third already discussed, in which it is stated that the squares of the times of revolution of any two planets, including the Earth, about the Sun are proportional to the cubes of their mean distances from the Sun. It was the disclosure of these wonderfully simple relations that laid the foundation for the Newtonian law of gravitation. Contemporary judgment, of course, could not anticipate the culmination of a later generation. What it could understand was that the first law of Kepler attacked one of the most time-honored of metaphysical conceptions, the Aristotelian idea that the circle is the perfect figure and that planetary motions, consequently, must be circular. Not even Copernicus had doubted the validity of this assumption. Kepler was too great a genius to rest content with the mere observation that the planets move in ellipses. Next, he desired to determine why they do so move. It remained for Isaac Newton, 1643 to 1727, to answer the question satisfactorily. Yet Kepler had a curious premonition of the law of gravitation. Quote, "Whereas the Ptolemaic system," unquote, comments Berry, quote, "required a number of motions round mere geometrical points, centers of epicycles or eccentrics, equants, etc., unoccupied by any real body, and many such motions were still required by Copernicus, Kepler's scheme of the solar system placed a real body, the Sun, at the most important point connected with the path of each planet, and dealt similarly with the Moon's motion around the Earth, and with that of the 4 satellites round Jupiter. Motions of revolution came, in fact, to be associated not with some central point, but with some central body, and it became therefore an inquiry of interest to ascertain if there were any connection between the motion and the central body. The property possessed by a magnet of attracting a piece of iron at some little distance from it suggested a possible analogy to Kepler, who had read with care and was evidently impressed by the treatise On the Magnet, De Magnete, published in 1600 by William Gilbert of Colchester, 1540 to 1603. He suggested that the planets might thus be regarded as sharing to some extent the Sun's own motion of revolution. In other words, a certain carrying virtue spread out from the Sun with or like the rays of light and heat, and tried to carry the planets around the Sun. Kepler says himself in his Epitome, quote, "There is therefore a conflict between the carrying power of the Sun and the impotence or material sluggishness, inertia, of the planet. Each enjoys some measure of victory, for the former moves the planet from its position, and the latter frees the planet's body to some extent from the bonds in which it is thus held, but only to be captured again by another portion of this rotary virtue." Unquote. Thus is faintly indicated the great theory of gravitation which, as developed by Newton, was to supply a satisfactory explanation of planetary motion, and which is the underlying basis of all modern astronomy. Newton had become convinced that the attracting power of the Earth extended even to the Moon, and that the acceleration produced in any body, whether it be as distant as the Moon or close to the Earth, was inversely proportional to the square of the distance from the Earth's center, and also proportional to the mass of the body. Then he found that the motions of the planets could be explained by an attraction toward the Sun, which produced an acceleration inversely proportional to the square of the distance from the center of the Sun, not only in the same planet, in different parts of its path, but also in different planets. Again, it follows from this that the Sun attracts any planet with a force inversely proportional to the square of the distance of the planet from the Sun's center, and also proportional to the mass of the planet. Accordingly, if the Earth or Sun attracts a body, the body must exert a similar force on the Earth or the Sun, and gravitation is not only a property of the central body of a revolving system, but belongs to every planet in just the same way as to the Sun and to a moon, or to a stone, just as to the Earth. After Newton had established provisionally the law of gravitation and the laws of motion, it remained for him to prove that the observed motions of the planets agreed with those calculated. A situation of the greatest complexity, however, was relieved by the fact that the mass of even the largest planets is so very much less than that of the Sun that the motion of any single planet is affected but slightly by the others, and it may be assumed to be moving very nearly as it would if the other planets did not exist, due allowance being made subsequently for minor disturbances or perturbations produced in its path. One by one the various irregularities observed were explained, and the motion of the Moon and its various eccentricities were computed with accurate numerical results. End of section 9.
Section 10 of The Science, History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Science, History of the Universe, Volume 1, edited by Francis Rolt Wheeler, Astronomy, Chapter 8, The Solar System, Part 2. For many years, the solar system remained in its fancied integrity. There was no change in the original 5 planets, and the number of satellites first discovered by Galileo and added to by subsequent observers had reached an apparent culmination when G.D. Cassini had detected the second pair of satellites of Saturn in 1684. Accordingly, when Herschel, following his custom of making a review of the heavens with each new telescope that he constructed, found March 13th, 1781, with a Newtonian telescope 7 feet in length, a small star which appeared so much larger than its companions and of such uncommon appearance, he suspected it to be a comet. Further study revealed that it was more than a comet and of far greater interest. When heedfully observed and its path calculated, it was found that no ordinary cometary orbit would in any way fit its motion. Anders Johann Lexell first recognized that Herschel's body was not a comet, but a new planet revolving around the sun in a nearly circular path and at a distance about 19 times that of the Earth and nearly double that of Saturn. A vain attempt by Herschel to name the new planet after his royal patron, George III, Georgium Sidus, finally resulted in the proposal and acceptance by British and continental astronomers alike of the name Uranus, which harmonized with the names of the other planets. This discovery was of especial interest, inasmuch as Johann Daniel Titius, a professor at Wittenberg, had pointed out the remarkable symmetry in the disposition of the planets. In a note published in 1772, he showed that the distance of the 6 known planets from the Sun could be represented with a close approach to accuracy by a certain series of numbers, increasing in the regular progression 0, 3, 6, 12, 24, 48, etc. Adding 4 to each number, the results would give the relative distances of the 6 known planets from the Sun. In applying this law, which does not hold good in the case of Neptune, it was found that the term of the series following that which corresponded with the orbit of Mars was not represented in the list of planets. Accordingly, Johann Elbert Bode, a German astronomer, assumed a hypothetical planet to take this place. When Uranus was discovered, its distance was found to fall but slightly short of perfect conformity with the law of Titius, and it stimulated the search for a new body, which, as will be seen in the chapter of the planetoids, proved to be the small planet Ceres. The study of Uranus, after its discovery by Herschel, furnished many discoveries to astronomers. Despite the most careful calculations of the movements of the planet through more than a century's observations, the conclusion was reached that considerable errors existed or that the planet was wandering from its course. In fact, these disturbances had aroused the interest of several mathematicians and astronomers, and a young English student, John Couch Adams, soon after his graduation from Cambridge, communicated in 1845 to the Astronomer Royal numerical estimates of the elements and orbits of the unknown planet, which he assumed was acting on Uranus and was the cause of the disturbances. In fact, he indicated the actual place in the heavens of the hypothetical planet. At practically the same time, a French astronomer, Urbain Le Verrier, who had made a careful study of the solar system in response to a request from Dominique F.J. Arago, the head of the French observatory, prepared an elaborate memoir in which he demonstrated that only an exterior body could produce the disturbances observed, and that such a body must occupy a certain and determinate position in the zodiac. He also assigned the orbit of the disturbing body, indicating that it would be as visible and bright as a star of the 8th magnitude. In fact, he supplied data to Professor Galle of the Berlin Observatory, which enabled that astronomer to find in the heavens on September 23, 1846, within less than a degree of the spot indicated, an object with a measurable disk. A reasonably complete map of this portion of the sky in which all the stars were noted, proved beyond question that the object was not a star, while its movement, as predicted, was ample confirmation of its planetary nature. Adams' work, which antedated that of Leverrier, had not received attention originally in Great Britain at the hands of the Astronomer Royal, but as the matter assumed importance, the Cambridge Observatory also participated in the search, and on September 29, 1846, the planet was seen again. Thus, Neptune was discovered. To show the rapidity of astronomical research in the 19th century, it may be remarked that it required but 17 days for the discovery of a satellite by Lassell with a 2-foot reflecting telescope. Astronomers have suspected the existence of still other planets, and the belief has been expressed that such a body exists nearer to the Sun than Mercury, which, as has been seen, enjoys the reputation of being the closest of all the planets to the central luminary. The average distance of Mercury from the Sun is about 36 million miles, so that there would be enough space for such a planet. Its peculiar position in close proximity to the Sun, however, would act against its being observed. A small luminous point in this position would be altogether invisible, even with the best modern telescope, while its setting and rising, simultaneous almost with those of the Sun, make it invisible at these times, even under the most favorable conditions. If this planet should pass across the Sun's disk, just as do Mercury and Venus, it would be seen. While from its size, it would be much less of a spectacle than the two planets mentioned, it might be detected. Claims have been advanced by astronomers that they have seen such a transit of a small spot. The first suggestion of an intramercurial planet came from the distinguished French astronomer Leverrier, who in 1859 advanced such a hypothesis in an attempt to explain the movements of the planet Mercury. His theory involved a body of about the size of Mercury revolving at somewhat less than half its mean distance from the Sun, or at a greater distance if of less mass, and vice versa, whose motion in great part would explain the irregularities observed. In the same year, Dr. Lescarbault at Orgères maintained that he had observed such a body crossing the Sun's disk, and the name of Vulcan was bestowed upon it. Several astronomers claim to have seen the new planet. Their observations were not well authenticated, and on the dates fixed for the probable transits, no trace of the planet could be found. The strongest test was the examination of the sky at the time of a solar eclipse, for then the light of the Sun was cut off, and a strange body could be readily identified. Despite a careful watch at subsequent eclipses and an examination of photographic plates, only negative results have been obtained. Today, the belief that there is any body of considerable size within the orbit of Mercury is held only by a few astronomers and very guardedly stated. If the search for an intramercurial planet was unsuccessful, it has in no way deterred astronomers from endeavoring to find other unrecognized members of the solar system. Much interest has been aroused by a hypothetical ultra-Neptunian planet, which of course would be the furthest from the Sun of all the members of the solar system. The basis for such a hypothesis is the reduction of observations made of the positions and motions of Uranus and Neptune. Neptune has been under observation for only a small part of a revolution, so that data thus far obtained seemed to many astronomers insufficient for the purpose. Yet a number of astronomers have sought by calculation to prove the existence of such a planet. While their results are discordant, yet they indicate very closely the regions of the sky where search for the hypothetical body might be rewarded with success. Professor W.H. Pickering of Harvard in 1909 evolved a method for the discovery of the distant planet, a method which he first tested by application of the data available to Adams and Leverrier for the discovery of Neptune, and found that the method would succeed. Proceeding then with his hypothetical planet, which he termed O, he found that it was 51.9 times as far distant from the Sun as the Earth, though its mass was but twice that of this planet, and that it had a period of revolution of 373.5 years. The problem presented by Uranus, Neptune, and O, according to Professor Pickering, is quite the same as that of Mercury, Venus, and the Earth, which has been thoroughly studied, so that the relative motions are well understood. But in investigating the effect that such a hypothetical planet would have on the motion of Uranus, Professor A. Gallo recently arrived at the conclusion that there were indications pointing to the possibility of still another and more distant planet also exercising a perturbing influence. The results of his calculations and studies therefore indicate the possible existence of two ultra-Neptunian planets, one at a distance from the Sun equal to 44 times the Earth's mean distance, and having a mass of about 1/64,000th the mass of the Sun, the other having a distance 66 times that of the Earth, and a mass of about 1/14,000th that of the Sun. While these figures disagree with those of Professor Pickering, yet the position calculated for the second planet agrees quite closely with that of the Harvard astronomer. The problem is by no means solved. It is mentioned to show that a plausible case has been made for at least one ultra-Neptunian planet. After astronomers had definitively decided how far the planets and the Sun are situated from the Earth and how they move with respect to one another, they began to wonder if perhaps the whole solar system did not in turn revolve around some central orb. The possibility first occurred to Tobias Mayer, Jean Michel, and Joseph Jérôme Lefrançois Lalande, but the problem was not attacked with any degree of success until William Herschel in 1782 began to draw conclusions from his study of the Milky Way, and decided that the entire solar system was drifting toward the constellation Hercules. But Herschel's theory did not meet with general acceptance for many years. Other astronomers suggested various stars as possible central suns controlling the movement of our solar system. Thus, Mädler not only proposed that Alcyone, the principal star in the Pleiades, should be the central sun because of its situation at a point of neutralization of opposing tendencies and consequently at rest, but even went so far beyond the limits of astronomy as to declare that, quote, "Here was the seat of the Almighty, the mansion of the Eternal," end quote. It is hard even for science to quell the imagination and to confine an observer to facts. Mädler's theory was short-lived. Further study of the stars demonstrated the soundness of Herschel's views. When a modern telescope is turned toward the Milky Way, this white girdle of the celestial sphere is resolved into a vast number of stars, of which more than 140 million already have been counted on photographs. Each of these stars is a sun like that which governs the Earth, probably surrounded by planets like the Earth. And all these solar systems also are moving, many of them more swiftly than ours. It was inferred from Herschel's measurements of stellar positions, distances, and motions that the solar system was situated comparatively near the center of a universe shaped like a thin double convex lens. This universe was supposed to rotate as a unit about its center, with the result that the sun, comparatively near that center but absolutely at an immense distance from it, moved in a circle of dimensions so vast that since the discovery of its motion, it had not deviated appreciably from a straight line, but had steadily directed its course toward the constellation Hercules. This simple scheme must now be abandoned, for it has been discovered by Professor J.C. Kapteyn, a Dutch astronomer, that the visible universe consists of two distant parts. The scientific imagination is compelled to picture two processions of stars moving in paths which make an angle of 115 degrees with each other. One of these stellar streams moves 3 times as fast as the other. The sun forms a part of one of the streams and is at present at their intersection. Although it is known in a general way that the entire solar system is moving through space at the rate of 12 miles a second, the shape and size of the sun's orbit are utterly unknown. The changes of environment, accordingly, that will accompany the description of it defy conjecture. The actual course of the solar system is inclined at a small angle to the plane of the Milky Way. Presumably, it will become deflected, but perhaps not sufficiently to keep the system clear of entanglement with the galactic star throngs. In the present ignorance of their composition, no forecast of the results can be attempted, They are uncertain and exorbitantly remote. Hence, in a sense, the world knows where it is and in what direction it is moving. But what is the goal? When shall it be reached? And what will happen then? Or, in this crossing of the congested thoroughfares of the heavens, will the world be shattered by a collision and resolved into a glowing nebula? This has been the fate of many stars, of several within the period of human history, and of one, Nova Persei, within a few years, and witnessed in all its destructive detail by astronomers still living. End of Section 10. Recorded by Dan Longauger in Washington State.
Section 11 of the Science History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Kay Hand. The Science History of the Universe, Volume 1, edited by Francis Rolt Wheeler. Astronomy. Chapter 9, The Sun, Eclipses, Sunspots and Aurorae, the Photosphere, Part 1. The preeminence of the Sun among the celestial bodies and its obvious importance to the life of the world has given to it a unique place, not only in astronomy but in philosophy and religion. The rising of the Sun and the light that it casts over the earth are distinctly symbolical of the conquest of light over darkness, or the triumph of truth over error, so that in many schemes of mythology the sun god assumes the highest rank and rules over the other elements, such as the moon, the rains and floods, and the stars. Of this there are abundant instances in all primitive religions. Among the Oriental nations, to whom we owe the idea of a flood from which the world emerged, the sun god reigned supreme. In Egypt, among the Chaldeans and Babylonians, and later among the Greeks and Romans, the sun held like sway. In Persia, sun worship was developed into a more formal religion, which survived for many years. After the mind of man had developed to a point where it was concerned with philosophical speculation rather than with the mysticism handed down by the priesthood, there came a desire to understand the relation of the sun to the earth and to the universe. Its motion across the sky was obvious, as well as its change of position from time to time. On this, as has been seen, various theories were founded. It was early realized that the sun described an annual path on the celestial sphere, which path is a great circle, and this great circle, known as the ecliptic, because eclipses take place only when the moon is in or near it, is at an angle to the equator of the sphere. This angle is termed the obliquity of the ecliptic, and was measured by the Chinese, it is claimed, as early as 1100 BC with remarkable accuracy. Later, the same feat was claimed for Pythagoras or Anaximander in the 6th century BC, both of whom probably derived their information from the Chaldeans or Egyptians. When the sun crosses the equator, the day is equal to the night, which occurs twice a year. At the vernal equinox about March 21st, and the autumnal equinox about September 23rd. When the sun is at its greatest distance from the equator on the north side, the time is known as the summer solstice, and when at its greatest distance on the south side, it is termed the winter solstice. The positions of these points in the heavens were also known to the early Chinese astronomers with considerable accuracy, while Anaximander, who supposed the sun to be of equal magnitude with the earth, used a gnomon, or vertical pillar, casting a shadow to observe the solstices and equinoxes. Anaximenes is said to have believed that the sun was a mass of red-hot iron or of heated stone somewhat larger than the Peloponnesus. He looked upon the heavens as a vault of stones, prevented from falling by the rapidity of its circular motion, while the sun could not proceed beyond the tropics on account of a thick and dense atmosphere which compelled it to retrace its course. Later, Philolaus of Crotona, who was a disciple of Pythagoras and followed his master's teaching that the earth revolved about the sun, assumed that the sun was a disk of glass which reflected the light of the universe. Eudoxus of Cnidus, about 370 BC, stated that the diameter of the sun was 9 times greater than that of the moon, which marked a triumph over the illusions of sense. About the time of Alexander, the great Pytheas, using the gnomon, determined the length of the shadows cast at the summer solstice in various countries. His observations are the most ancient of those preserved, after those made in China. The study of the sun was undertaken very systematically by Hipparchus, who discovered that the solar orbit was eccentric and that the sun moved at different speeds at different parts of its journey. With his observational data, Hipparchus produced the first tables of the sun which are mentioned in astronomy. He was enabled to determine the difference between the solar day, or time as shown by the sun, and the time indicated by some such measuring device as the clepsydra, or water clock. The motion of the sun was also studied by Ptolemy. He compiled solar tables more extensive than those of Hipparchus, which were employed until Albategni, born 815, made a new compilation of greater accuracy, and which served as a connecting link between the astronomers of Alexandria and those of modern Europe. The obliquity of the ecliptic was constantly being studied. Ulu Beg, a Tartar prince and grandson of the great Tamerlane at Samarkand, using a gnomon 100 feet in height, determined the obliquity of the ecliptic or precession of the equinoxes, and secured data for the construction of astronomical tables which were of considerable accuracy. The apparent motions of the sun furnished many difficult problems for the astronomer, since the observational data lacked accuracy on account of the absence of satisfactory instruments. Measuring angles by the shadow cast and positions in the sky by crude forms of angular measurement were not adequate for exact work. Not until the advent of the quadrant and the telescope with its various adjuncts was scientific measurement possible. But there were from time to time solar eclipses, of which a careful record was maintained and which the ancient priests noted in connection with their calendar observations. These eclipses played a most important part in ancient astronomy. An eclipse of the sun occurs when Earth, Moon, and Sun are in direct line at the time of new moon. As the latter lies between the Earth and the Sun, its dark body will pass across the Sun's disk, cutting off the direct illumination. If the Earth cuts off the sunlight from the Moon, there is a lunar eclipse. Solar eclipses are of three kinds: partial, annular, and total. In the first, the Moon, instead of passing directly between the Earth and the Sun, slips past on one side and cuts off from sight only a portion of the Sun's surface. In the annular eclipse, the Moon is centrally interposed between the Sun and the Earth, but falls short of the apparent size required to conceal the solar disk entirely. Consequently, at the height of obscuration, a bright ring is visible around the Moon. In a total eclipse, however, the Sun completely disappears behind the dark body of the Moon. The difference between a total and an annular eclipse depends upon the fact that the apparent diameters of the Sun and the Moon are so nearly equal as to preponderate alternately one over the other through the slight periodical changes in their respective distances from the Earth. It is the total eclipse that particularly arouses the attention of astronomers, for it cuts off entirely the light of the Sun, and in addition to enabling the observation of the various parts of its surface as it passes across its disk to be made, also makes it possible for an observer to see the stars and planets in the daytime, even if they are very near to the Sun. A total eclipse of the Sun is not visible on the entire Earth, but only along a comparatively narrow band, lying roughly from west to east and measuring about 165 miles in width. A partial eclipse is seen for about 2,000 miles on either side of this band, but otherwise the phenomenon is not visible on the Earth's surface. Chinese records going back over 4,000 years describe a solar eclipse which occurred during the 22nd century BC. That eclipse carried with it a distinct moral lesson. Two bibulous state astronomers, Ho and He, unfortunately happened to be drunk on the day of its occurrence, and hence incapable of supervising the performance of the required rites, which consisted in beating drums, shooting arrows, and other ceremonies intended to frighten away the mighty dragon who was about to swallow up the Lord of Day. Although the eclipse was only partial, nevertheless great confusion resulted, and Ho and He were put to death as a lesson to later astronomers. Another early record of a total eclipse comes from Babylon, 1063 BC. Several centuries later, Assyrian tablets record solar eclipses. Herodotus, Plutarch, and the Bible all refer to the phenomenon. Thus, one is enabled to determine with accuracy the time of historical events. Likewise, in the Anglo-Saxon chronicles, several notable eclipses are recorded. The Sun appears as a brilliant white body. Just as the Earth is enveloped by an atmosphere, so the Sun is surrounded by several layers of gaseous and vaporous matter, with the result that so far as an observer on the Earth is concerned, its nucleus is quite invisible. These layers are more or less transparent, just as the atmosphere of the Earth is transparent, so that the bright white body of the Sun is visible only through these various envelopes. This bright white portion is called the photosphere, and is the source of the light and heat which is radiated to the Earth. Here are found the sunspots distinctly seen with the telescope and even by the naked eye. Under the photosphere it may be that the more solid portions of the Sun are situated, but it is obvious that its surface consists of highly incandescent vapors above which is a smoke-like haze. Upon this rests the reversing layer, which is composed of glowing gases, but is cooler than the photosphere beneath. It has a thickness of between 500 and 1,000 miles and contains, as the spectroscope shows, many of the elements of which the Earth is composed, in the form of vapor. Above the reversing layer comes the chromosphere. The chromosphere is between 5,000 and 10,000 miles in thickness and is composed of glowing gases, chief among which is hydrogen. The chromosphere is a brilliant scarlet in hue, but the redness is entirely overpowered by the intense white light of the photosphere, which shows through from behind. The most interesting features of the chromosphere are the red prominences, which are the marks of violent agitation in its upper portions, and which are such a notable feature in total solar eclipses. After the chromosphere comes the corona, which is the outer envelope of the Sun, and consists of a halo of pearly white light of irregular outline, which fades away into the surrounding sky and extends outward for many millions of miles. The corona suffers so much from the brilliancy of the photosphere that it is only on the occasion of a total solar eclipse that it can be seen in all its remarkable beauty. As the photosphere, the reversing layer, and the chromosphere are all sources of light, the solar spectrum observed in spectroscopes is composed of the three separate spectra combined. For this reason, eclipses afford welcome opportunities for studying the Sun's surface. When the Moon completely covers the photosphere, its brilliant light is cut off, and the other features of the Sun can be examined visually, and, what is more important, spectroscopically and photographically. Thus, when the spectroscope is directed to the reversing layer during a total eclipse, the dark lines of the solar spectrum change into bright lines, or are reversed. But this reverse spectrum is a phenomenon of a moment only, and as the Moon progresses, an altered spectrum is obtained. That of the chromosphere is of sufficiently long duration to permit an estimate of its depth and nature, and finally, when this is covered up, there is the corona, which has a distinct spectrum of its own, containing a strange line, the distinguishing green of which has not yet been identified with any element known upon the Earth. Modern conceptions of the Sun are due very largely to the use of the telescope, the spectroscope, and the spectroheliograph, especially the last two instruments. With this telescope, when the intense light of the Sun is properly reduced, it is possible to examine its surface and obtain a certain amount of information as to its nature, or to obtain photographs of that surface by very short exposures. But on the spectroscope and the spectroheliograph, the astronomer depends for his knowledge of the constitution and composition of the greater center of the solar system. The development and nature of the spectroscope, as used in solar research, have been already discussed. But it is appropriate to add here a brief explanation of the spectroheliograph, for to its use is due not only a large part of present-day information of the prominences, but more recently an explanation of the sunspots themselves and the study of various features of the photosphere. The spectroheliograph was first devised in successful working form by Professor George E. Hale at Kenwood Observatory, Chicago, in 1889. The principle of this instrument is very simple, writes Professor Hale. Its object is to build up, on a photographic plate, a picture of the solar flames by recording side-by-side images of the bright spectral lines which characterize the luminous gases. In the first place, an image of the Sun is formed by a telescope on the slit of a spectroscope. The light of the Sun, after transmission through the spectroscope, is spread out into a long band of color, crossed by lines representing the various elements. At points where the slit of the spectroscope happens to intersect a gaseous prominence, the bright lines of hydrogen and helium may be seen extending from the base of the prominence to its outer boundary. If a series of such lines corresponding to different positions of the slit on the image of the prominence were registered side by side on a photographic plate, it is obvious that they would give a representation of the form of the prominence itself. To accomplish this result, it is necessary to cause the solar image to move at a uniform rate across the first slit of the spectroscope, and with the aid of a second slit, which occupies the place of the ordinary eyepiece of the spectroscope, to isolate one of the lines, permitting the light from this line and from no other portion of the spectrum to pass through the second slit to a photographic plate. If the plate be moved at the same speed with which the solar image passes across the first slit, an image of the prominence will be recorded upon it. The same method answers for the study of the sunspots and other features of the sun's surface. As the result of telescopic, spectroscopic, and spectroheliographic observation, it is now known that the sun's principal features are its sunspots, its photosphere, its chromosphere, and its corona. A sunspot, when examined through a telescope, consists of a dark central region called the umbra, into which long, narrow filaments reach. The space occupied by these filaments is termed the penumbra. The darkness of the umbra is not absolute, but is relative to the more brilliant surface of the photosphere, and if observed alone, would be far more brilliant than the most powerful arc light. These dark spots on the sun were familiar objects in the days of pre-telescopic observation, but their importance to astronomy dates with their discovery in 1610 by Galileo with his telescope. The great Italian astronomer did not announce his discovery until May 1612, by which time sunspots had been seen independently by Thomas Harriot, 1560 to 1621, John Fabricius, 1587 to 1615, who published his observations in June 1611, or before Galileo, and the Jesuit father Christopher Scheiner, 1575 to 1650, all of them pioneer observers with the telescope. End of section 11. Section 12 of the Science History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by K. Hand. The Science History of the Universe, Volume 1, edited by Francis Rolt Wheeler. Astronomy. Chapter 9, The Sun, Part 2. Before sunspots were clearly observed with the telescope, it was assumed that they were due to the transit of Mercury. Even Father Scheiner, after his telescopic studies, suggested that the spots might be small planets revolving around the sun and appearing as dark objects whenever they passed between the sun and the observer. It was recognized, however, that the spots appeared to move across the face of the sun from the eastern to the western side, or roughly from left to right. Father Scheiner's view was also held by Jean Tarde, canon of Sarlat, by Father Malpertius, a Belgian Jesuit, and later by William Gascoigne, the inventor of the micrometer. Galileo, however, advanced a cloud theory, while Simon Marius, astronomer and physician to the brother Margraves of Brandenburg, proposed the ingenious slag theory, according to which the dark spots were the cindery refuse of a great solar conflagration, and occasionally expelled in the form of comets, which afterward blazed up with renewed vigor. Galileo, in a controversy with Father Scheiner, proved him wrong in his planetary theory, while the occurrence of the comets in 1618 won supporters for the theory of Marius. Galileo also ascertained the rotation of the sun in a period of between 25 and 26 days, as well as the general zone of the sunspots. The next important contribution to sunspot theory came from Durham, whose observations were made during the years 1703 to 1711. He believed that the spots on the sun were caused by the action of some new volcano, whose smoke and other opacious matter produced the spots. As they decayed, they became half-shadows encircling the darker portions and finally became bright spots. Lalande, the celebrated French astronomer, believed that the spots were rocky elevations, about which the penumbra represented shoals or sandbanks, while around flowed enormous oceans. Lalande's explanation, as well as that of Durham, was clearly based upon terrestrial analogies, which were employed with considerable frequency by early astronomers. In 1769, Alexander Wilson of Glasgow, 1714 to 1786, examining the large sunspot visible that year, noted that as the sun's rotation carries a spot across its disk, there was a change in its appearance, and that the same effect of perspective was produced as if it were a saucer-shaped depression, the bottom forming the umbra or central black spot, and the sloping sides the penumbra or surrounding portion of half-shadow. The penumbra appeared narrowest on the side nearest the center of the sun and widest on the part nearest the edge. Hence Wilson assumed that the great and stupendous body of the sun is made up of two kinds of matter, very different in their qualities, that by far their greater part is solid and dark, and that this immense and dark globe is encompassed by a thin covering of that resplendent substance from which the sun would seem to derive the whole of his vivifying heat and energy. Wilson went on to explain that the excavation of spots might be occasioned by the working of some sort of elastic vapor which is generated within the dark globe, and that the luminous material, which was more or less fluid, was acted upon by and tended to throw down and cover the nucleus. Sir William Herschel devoted considerable attention to the sun, and observing the variation in the sunspots, reached the conclusion in 1801 that it indicated a certain variability in the total amount of solar radiation, which he assumed might have some connection with terrestrial phenomena, especially the weather. He endeavored first in 1801 to trace connection between the price of wheat, naturally influenced by the effect of weather on the crops, and the occurrence of sunspots, claiming that when the latter were scarce there was a diminished solar activity, which caused colder weather, with obvious results. Ingenious as this theory was, there were not sufficient substantiating meteorological data. It finds, however, a counterpart in modern studies of the sun's heat, not necessarily connected exclusively with sunspots, however, whereby it is hoped to establish some useful knowledge of the relation between the amount of heat radiated from the sun and weather conditions on our earth. Herschel's observations of the sun and sunspots were continued by his son, Sir John Herschel, at the Cape of Good Hope, 1836 to 1837. John Herschel assumed that their motion was due to fluid circulations similar to those producing the trade and anti-trade winds on the earth. The spots, in this view of the subject, he said, would come to be assimilated to those regions on Earth's surface where for the moment hurricanes and tornadoes prevail, the upper stratum being temporarily carried downward, displacing by its impetus the two strata of luminous matter beneath, the upper, of course, to a greater extent than the lower, and thus wholly or partially denuding the opaque surface of the sun below. Such observation of sunspots, made with considerable thoroughness by the astronomers mentioned, as well as numerous others, did not establish any regularity in their appearance or effacement. It remained for Heinrich Schwab, 1790 to 1875, at Dessau, to announce in 1843 that the sunspot phenomenon reached a maximum probability in a decennial period. This announcement, although coming as it did after a patient study of the sun, attracted no particular attention until a series of sunspot statistics were published in Humboldt's Cosmos. Then the correctness of Schwab's observations and deductions was apparent to all. When compared by Dr. John Lamont and Sir Edward Sabine with various periodical magnetic disturbances, it was found that the two cycles of changes agreed with extraordinary exactness. It was a remarkable coincidence that the observations of a number of investigators were in complete harmony. A study of sunspot records established the decennial period more correctly at 11.11 years. Thus commenced a recognition that magnetic disturbances on the Earth were related in some way to sunspot phenomena. For many years, no direct connection could be established, although various theories were forthcoming. Likewise, further attempts were made to identify the variations of sunspots with meteorological phenomena, but without success, until Wolf in 1859, by an examination of the Zurich Chronicles, 1000 to 1800 A.D., found data which established occurrences of the aurora borealis to be correlated with a disturbed condition of the sun. From this time on, the influence of the sun on terrestrial conditions assumed new importance. The beautiful phenomenon of the aurora, which consists of a glow in the sky about the north and south poles, had been observed for ages, but the first scientific connection of importance recorded was in 1716, when Halley stated that the northern lights were due to magnetic effluvia. In 1741, Hiorter at Uppsala observed that they produced an agitation of the magnetic needle. This connection was further demonstrated by Arago, 1819, so that by the middle of the 19th century the connection of the aurora with the sun, and in turn with terrestrial magnetism, was as evident as it was insufficiently explained. The first result of modern study of the sunspots was to put an end to the old notion that there was a dark and cold interior of the sun, and that the sunspots were merely rents in the brilliant cloud covering through which the interior portion could be seen. The late Professor S. P. Langley, one of the most active of the modern students of the sun and its surface, thought that the filaments, which taken together constitute the penumbra, were everywhere present on the surface. Professor Hale states, he regarded them as resembling the stalks of a wheat field seen on end in the undisturbed photosphere, and revealing more of their true characteristics in the penumbra, where they are bent over and drawn out toward the central part of the spot. Langley believed that we are observing clouds of luminous vapors rising from the sun's interior, the seats of convection currents which bring to the surface the immense supplies of heat radiated by the sun into space. Separating these luminous columns are darker regions, characterized by a lower degree of radiation. The minute details can be recorded only with the greatest difficulty. Under ordinary atmospheric conditions, the solar image is not seen as a sharp and well-defined object, but its details are continually blurred by the effect of irregularly heated currents in our atmosphere. Even under the best conditions, the moments of very sharp definition are few, and the greatest patience and perseverance are required on the part of an observer who would record his impressions of the solar structure. At the best, drawings based upon visual observations must be unsatisfactory, since even the skilled hands of Langley could not secure the perfect precision which is so desirable. It accordingly might be hoped that here, as in other departments of solar research, photography would afford the necessary means of securing results unattainable by the eye. Unfortunately, however, this hope has only been partially realized. The influence of sunspots is not confined to magnetic and electrical phenomena. The researches of Koppen, which have been confirmed by Newcomb, show that the average temperature of the Earth, determined by the combination of a great number of thermometric observations made at several stations, indicated a fluctuation of 0.3 degrees to 0.7 degrees Celsius during the 11-year sunspot period. In other words, the temperature of the Earth's atmosphere indicates small fluctuations which correspond with the sunspot period, thus indicating that the solar heat radiation varies with the number of the sunspots. The mean temperature of the Earth is greatest at the time of minimum sunspots and lowest at the time of maximum sunspots. Hence the determination of the amount of heat radiated by the sun at various times, especially at sunspot maxima and minima, is a matter of considerable terrestrial importance. The study of the sunspots, carried on by Professor Hale with the spectroheliograph and other apparatus, including special red-sensitive plates of considerable speed, reached an interesting stage in 1908 when it was demonstrated that sunspots are centers of attraction which draw toward them the hydrogen of the solar atmosphere. Subsequently, it was found that these spots are the seats of great cyclones, in which cool hydrogen gas is set whirling and is sucked down in the great maelstrom of the sun, rushing into the center of the spot at a rate of about 60 miles a second. Consequently, the spots are the center of great solar disturbances which are of an electromagnetic nature. According to the modern electronic theory of matter and electricity, electrons, or minute particles of matter, in their terrific cyclonic velocity, produce magnetic lines of force. It was found by Professor Zeeman that when light is passed through a strong magnetic field, the lines of the spectrum are subdivided and appear double. This Zeeman effect Professor Hale has found in the spectrum of the sunspots. If one looks at the center of a spot, the light travels in the direction of the axis of the whirl or cyclone, while in viewing a spot at the edge of the sun, the direction is at right angles to the axis and is manifested accordingly in the spectrum. This theory has been thoroughly confirmed, so that today it is known that sunspots are magnetic fields of great intensity. The important discoveries made by Professor Hale and his associates may thus be summarized as follows. First, that the spots are cooler than the surrounding region. Second, that they are centers of violent cyclones. And third, that they are magnetic fields of great intensity. In addition to the sunspots, the photosphere includes other interesting features, notable among which are the faculae, little torches, so named by Father Scheiner. These bright globular objects, besides the sunspots, are the only other phenomena of the sun's surface visible by direct observation. Schroeder showed that the faculae are heaped up ridges of the disturbed photospheric matter. Secchi and Young assumed that the faculae are the result of violent eruptive action of the sunspots, but it remained for the spectroheliograph to give a clear idea of their nature. Professor Hale states that they are usually most numerous in the vicinity of sunspots, and near the sun's limb they are sometimes very conspicuous, brilliant objects covering large areas. Near the center of the sun, however, they are practically invisible, though faint traces of them can sometimes be made out on photographs taken with suitable exposure. This increase of brightness toward the sun's limb is assumed to be due to the elevation of the faculae above the photospheric level and their escape from a considerable part of that absorption which so materially reduces the brightness of the photosphere. Rising above the denser part of the absorbing veil and thus suffering but little diminution of light, they appear near the sun's limb as bright objects on a less luminous background. The chief difference of the faculae from the rest of the photosphere lies in their greater altitude, as photographs have shown that they may be resolved into granular elements similar to those constituting the photosphere. But they are the regions from which immense masses of vapors rise to the solar surface, and for that reason are important in the solar mechanism. Near the edge of the sun, their summits lie above the lower and denser part of that absorbing atmosphere which so greatly reduces the sun's light near the limb, and in this region the faculae may be seen visually. At times they may be traced to considerable distances from the limb, but as a rule they are inconspicuous or wholly invisible toward the central part of the solar disk. The Kenwood experiments had shown that the calcium vapor coincides closely in form and position with the faculae, and hence the calcium clouds were long spoken of under this name. In the new work at the Yerkes Observatory, the differences between the calcium clouds and the underlying faculae became so marked that a distinctive name for the vaporous clouds appeared necessary. They were therefore designated flocculi, a name chosen without reference to their particular nature, but suggested by the flocculent appearance of the photographs. With the spectroheliograph, Professor Hale relates, it was at once found possible to record the forms, not only of the brilliant clouds of calcium vapor associated with the faculae and occurring in the vicinity of the sunspots, but also of a reticulated structure extending over the entire surface of the sun. From a systematic study of spectroheliograph negatives, in the course of which the heliographic latitude and longitude of the calcium clouds, or flocculi, in many parts of the sun's disk were measured from day to day by Fox, a new determination of the rate of the solar rotation in various latitudes has been made. This shows that the calcium flocculi, like the sunspots, complete a rotation in much shorter time at the solar equator than at points nearer the poles. In other words, the sun does not rotate as a solid body would do, but rather like a ball of vapor, subject to laws which are not yet understood. End of section 12.
Section 13 of the Science History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Edward Labonte. The Science History of the Universe, Volume 1, edited by Francis Rolt Wheeler, Astronomy, Chapter 10, The Sun, 2, The Reversing Layer, the Chromosphere and Corona, Radiation Pressure and Solar Energy, Part 1. The so-called reversing layer was discovered by the late Professor Charles A. Young during the eclipse of December 22, 1870, on which occasion he placed the spectroscope with its slit tangential to the sun's limb so that it ran along a shallow bed of incandescent vapors. When the moon reduced the size of the crescent of the sun, the dark lines of the spectrum and the spectrum itself gradually faded away until all at once, as suddenly as a bursting rocket shoots out its stars, the whole field of view was covered by bright lines, more numerous than one could count. This phenomenon lasted about 2 seconds and gave the impression of a distinct reversal of the Fraunhofer spectrum, showing bright lines for dark in every case. That such a reversing layer should exist was demanded by Kirchhoff's theory of the production of the Fraunhofer lines and implied a stratum of mixed vapors at a lower temperature than that of the surface of the Sun. It was by such a stratum that the missing rays of the solar spectrum were stopped. The spectrum from this portion alone could supply bright lines if the overpowering brilliancy of the solar background could be cut off, which can occur only at the time of an eclipse. This observation of Professor Young's, with its important bearing on the theory of Kirchhoff, was not confirmed until 1896, when photographic evidence was forthcoming. During the eclipses of 1898 and 1900, abundant corroborative material was obtained, and the reversing layer as a reality was conclusively demonstrated. The total depth of this reversing layer has been placed at from 500 to 600 miles. It continues in a normal state of tranquility, for little change is produced in the aspect of the dark lines. The chromosphere, or envelope of glowing gases, which covers the Sun completely, was detected by observers of eclipses in the 18th and 19th centuries. There is a record in a letter from Captain Stannyan to Flamsteed, the British Astronomer Royal, describing an eclipse witnessed at Bern on May 1st, Old Style 1706, in which he states that the Sun's, quote, getting out of the eclipse was preceded by a blood-red streak of light from its left limb, unquote. Halley and de Louisville in 1715 noted a similar phenomena, and it was also observed during annular eclipses of 1737 and 1748, but with the ruby brilliancy toned down to brown or dusky red by the surviving sunlight. During the eclipses of 1820, 1836, and 1838, similar observations were made, but it was not until the eclipse of the 8th of July, 1842, that the virtual discovery of the chromosphere as a solar appendage may be said to have been made. The eclipse of 1868, which was observed spectroscopically and photographically, as well as with the telescope, served to make clear the nature of the chromosphere and to reveal that it is a continuous envelope of hydrogen and other incandescent gases, some thousands of miles in thickness, and of the same eruptive nature as the prominences which are shot out from it. In other words, it seems to be a collection of minute flames set close together and giving it the appearance of a large conflagration. The summits of the flames of fire, which incline when the Sun's activity is greatest, are erect during its phase of tranquility. The chromosphere is marked by an irregular distribution over the Sun's surface, which in no way partakes of the character of an atmosphere. Professor Hale, in 1897, discovered a low stratum of carbon vapor. Such rare metals as gallium and scandium have been discovered with the spectroscope. The vapors of magnesium, iron, and several other substances are conspicuously represented in the spectrum of the chromosphere, and with the Yerkes telescope, the fine bright lines due to the vapor of carbon also may be seen. The solar prominences are conspicuous, eruptive, or flame-like emanations from the chromosphere which are seen at total eclipses of the Sun. They project like red flames beyond the dark edge of the Moon, and were first described by Lector Vesenius, a Swedish professor of Gothenburg, who observed the total eclipse of May 2nd, Old Style, 1733. One of these reddish clouds outside of the solar disk was so large that it could be detected with the naked eye. The phenomenon excited his admiration and wonder. The prominences were also observed in 1778 by the Spanish Admiral Don Antonio Ulloa, who was convinced of their connection with the Sun on account of their color and magnitude. By some observers, the solar prominences were regarded as the illuminated summits of lunar mountains, and by Arago they were described as solar clouds shining by reflected light. Abbé Pétal in 1842 spoke of them as self-luminous and as a third or outer solar envelope composed of the glowing substance of the bright rose tint, which produced mountains, just as clouds were piled above the Earth's surface. In 1851, Hind, an English astronomer, noted on the south limb of the Moon, quote, a long range of rose-colored flames, unquote, which Dawes spoke of as a low ridge of red prominences resembling in outline the tops of a very irregular range of hills. Airy also noted this rugged line of projections and spoke of its brilliancy and nearly scarlet color. But the truly solar origin of the phenomena was not conclusively demonstrated until 1860, when the prominences were photographed by Secchi and De La Rue and shown to be independent of the motion of the moon. In 1868, with the growth of spectroscopy and solar chemistry, the gaseous nature of the prominences and their connection with the sun was made evident. They were found to consist of immense masses of hydrogen and helium gas rising from the chromosphere and reaching an altitude of hundreds of thousands of miles. The corona. The corona is a beautiful, lustrous solar wrapping which can be observed only during a total eclipse. The winged circle, the winged disk, or the ring with wings, as it is variously called, found upon Assyrian and Egyptian monuments, may be reproductions of the phenomenon. The first definite mention of a solar corona is to be found in Plutarch in connection with the eclipse, which probably took place in 71 AD. He writes that the obscuration caused by the moon, quote, has no time to last and no extensiveness, but some light shows itself around the sun's circumference, which does not allow the darkness to become deep and complete, unquote. Kepler mentions a ray of light seen around the eclipsed sun in 1567 and ascribes it to some sort of luminous atmosphere around the sun. In 1706, Cassini, observing an eclipse of the sun in France, saw the, quote, crown of pale light, unquote, around the lunar disk, and stated that it was caused by the illumination of the zodiacal light. Halley, observing an eclipse in London in 1715, describes minutely the phenomena of the luminous ring rising around the moon to a great height and showing considerable brilliancy. The eclipse of 1842 was the first to indicate the corona's great importance to astronomers, and from that date it received careful attention and earnest study. In 1869, Professor Harkness and Professor Young discovered a bright line of unknown origin in the coronal spectrum, showing that it consists in large part of glowing gases. With the advent of astronomical photography and with the development of the spectroscope, more attention than ever was given to the careful study of the corona in the limited time available on the occasion of a total eclipse. The corona is described by Professor Hale as a, quote, faintly luminous veil of light extending outward in long streamers from the surface of the photosphere to distances of several millions of miles and exceeded in brilliancy, even in its brightest parts, by the full moon. In many ways, its streamers resemble those of the aurora borealis, and it is indeed possible that their origin may be ascribed to some similar electrical cause. During the few minutes of a total eclipse, they are not seen to undergo change of form, but the outline of the corona does vary greatly from year to year in sympathy with the general variation of the solar activity. Spectroscopic observations have shown that the corona consists mainly of gases unknown to the chemist. That is to say, the lines in its spectrum do not coincide in position with the lines of any terrestrial element. Whether these gases, which are probably very light, will ultimately be found on the Earth cannot be predicted. Like helium, first known in the Sun, they may eventually be encountered in minute quantities in some mineral, where they have hitherto escaped the chemist's analysis. The fact that the lower part of the corona gives a continuous spectrum, with a feebler solar spectrum superposed upon it, indicates that minute incandescent particles are present, which are hot enough to radiate white light and which scatter enough sunlight to account for the presence of the solar spectrum, unquote. The strange line in the green portion of the spectrum does not correspond with that of any element with which we are acquainted upon the Earth, and accordingly a hypothetical element has been assumed to which the name coronium has been applied. Chemical composition. Anaximenes' idea that the sun was a glowing ball of incandescent iron came almost as near the truth as subsequent speculations by philosophers and astronomers until about the middle of the 19th century. In 1859, Kirchhoff's great discovery of the explanation of the Fraunhofer lines in the solar spectrum made it possible to ascertain the chemical composition of the Sun. Thus, as has been shown, the bright-colored band formed of light from a small hole in Newton's shutter passing through a prism made that prism the forerunner of an instrument able to teach the nature and constitution of bodies far distant in the heavens. Thomas Melville had examined with a prism various flames in which different substances had been introduced, and had reached the conclusion by the middle of the 18th century that certain vapors, notably sodium, contained light which had a definite place in the spectrum. Melville's deep yellow ray became the sodium line in the spectroscope of Fraunhofer. When Kirchhoff noted the identity of certain lines characteristic of terrestrial elements and then assumed their presence in the Sun, he laid the foundation of the modern science of solar chemistry. Wherever light can be observed from a heavenly body, it is now possible to resolve it into its spectral elements and thus to identify the substances. In fact, as substances such as helium were found in the Sun by Lockyer, which had no terrestrial counterpart, hypothetical elements were assumed. The spectroscope has shown in the Sun the presence not only of gases such as hydrogen and helium, but iron, sodium, magnesium, calcium, and many other substances. Hence, the chemical composition of the Earth and the Sun are much the same, although there is evidence of the existence in the Sun of substances not yet found in the Earth. When the spectroscope was applied to the analysis of the chromosphere and its prominences, it was found that they are composed of the vapor of calcium and of the light gases helium and hydrogen. Sunspots, too, have been found to have a characteristic chemical composition, while the corona emits rays which probably indicate the presence in it of very light and tenuous gases. With the light given off by the Sun, there is to be considered a phenomenon which only recently has been demonstrated by experiment, namely that light exerts a pressure which can act on minute particles quite as effectively as gravitation. Gravitation, however, attracts entire masses, but pressure acts only on surfaces, so that a force, such as the pressure of light, to be effective must deal with very minute masses. If you subdivide a mass into a large number of minute particles, the effect of gravitation is not changed, but a point will be reached in the subdivision where particles may be obtained having much surface and very little weight. If such a particle has a diameter of 1/100,000th of an inch, it will be exactly balanced in space, pulled by gravitation, weight on the one hand, pushed by light on the other. If the particle is even smaller than 1/100,000th of an inch in diameter, the pressure of light upon it pushes it away with terrific force. It is the radiation of the Sun acting on the minute particles that produces the phenomenon of comets' tails, and it is this pressure which may be responsible for the brilliant phenomena of the corona, visible only during the vanishing moments of a total eclipse. No one has ever satisfactorily explained how the highly attenuated matter composing both the prominences and the corona is supported without falling back into the Sun under the pull of solar gravitation. Now that Arrhenius has cosmically applied the effects of light pressure, a solution is presented. How difficult it is to account for such delicate streamers as the prominences on the Sun is better comprehended when we fully understand how relentlessly powerful is the grip of solar gravitation. The Sun admittedly projects vapors into space, vapors which must condense into drops when they encounter the cold of outer space. If the drops are larger than the critical size which determines whether light pressure or gravitation shall prevail, they will be snatched back by the Sun's gravitational attraction and give rise to the curved prominences that are often observed. If they have approximately the critical diameter, they will float above the Sun in the form of beautiful carmine clouds, balanced in space by the equal and oppositely acting forces of gravitation and radiation pressure. These clouds have hitherto been particularly puzzling, for in the absence of a dense solar atmosphere, their existence seemed a celestial paradox. If the condensed drops are smaller than the critical diameter, they will be projected by the pressure of light far beyond the Sun to form the beautiful pearly corona. From the fact that comets have passed through the corona without any very apparent retardation, some idea of its tenuity can be gained. Assuming that the corona consists of particles of such size that the radiation pressure on each exactly equals its weight, Arrhenius finds that the entire corona weighs no more than 12 million long tons, which is equivalent to 400 large transatlantic steamers and is not more than the amount of coal burned on the Earth every week. Compared with the infinity of the space in which it is poised, the Earth is smaller than a vanishingly small speck on a sheet of paper having an area of many square miles. So far as the Earth is concerned, the Sun is very much in the position of a man who throws away all but a single cent of a fortune consisting of $23 million for only 1/2,300,000,000th of his radiated energy reaches this globe. What then becomes of the huge number of corpuscles which are shot from the Sun and which never strike the Earth? It is conceived by Arrhenius and his followers that many of them must collide with corpuscles discharged by suns other than that of this solar system, suns ineffably distant, so that their light reaches the Earth only after the lapse of countless centuries, and so that they are seen not as they gleam now, but as they gleamed when Egypt was young, and Greece was a wilderness inhabited by savages. Such collisions must result in the formation of large masses up to a limit determined by the electrical charges carried by the corpuscles. End of section 13.
Section 14 of the Science History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by K. Hand. The Science History of the Universe, Volume 1, edited by Francis Rolt Wheeler. Astronomy. Chapter 10, Solar Energy, Part 2. Solar energy. The Earth depends upon the Sun for its supply of heat and light. The Sun is transmitting heat to the Earth, and unless the supply of energy is being replenished in some way, it is obvious that it must be losing in heat and temperature. From its effect on the Earth, an estimate can be had of the amount of heat radiated by the Sun annually. If it be assumed that the Sun has the same heat capacity as water, and hydrogen is the only substance with a greater heat capacity, it would fall in temperature about 4 degrees Fahrenheit annually. If, therefore, the great luminary were simply a hot body, cooling off, its present rate of radiation could not be maintained for more than 3,000 years. That the Sun has been radiating a much longer period than this is obvious from geological and biological evidence, so that some other cause must be sought. Up to the 19th century, the doctrine of infinite durability was generally held by astronomers and geologists. For that reason, no particular attention was paid to the nature of the heat of the Sun and its source, but with the formulation of the doctrine of the conservation of energy, it was realized that the energy of the Earth must proceed from the Sun for the greater part, and consequently it became necessary in turn to question the source of solar heat. Robert Mayer, to whom is due the earliest conception of the conservation of energy, asked himself, "If the Sun is hot, why does it not cool off?" In 1848, Mayer published some answers to his own question in a paper which failed to receive the approval of the French Academy of Sciences. His conclusions were as follows. The Sun cannot be a glowing mass sending out radiation without compensation. Solar heat cannot be due entirely to chemical changes, nor can it be due to solar rotation. In his opinion, it was the result of meteors falling into the Sun. He did not overlook the fact that the resulting increase in the mass of the Sun would increase its attraction for the planets and would shorten the sidereal year. This was contrary to the facts of observation, and Mayer was forced to an incorrect conception of the undulatory theory of light to explain the situation. 6 years later, William Thomson, subsequently Lord Kelvin, reached independently almost the same conclusion as Mayer, but he was able to explain the increase in the sun's mass resulting from meteoric showers. For according to the gravitation theory, the added matter is drawn from space, where it acts on the planets with very nearly the same force as when incorporated in the sun. Lord Kelvin then ventured an estimate of the age of the sun, which was the first attempt in this direction made by a physicist. He assumed that the solar energy of rotation was derived from the fallen meteors, which, allowing for the constant loss of solar energy by radiation, could be acquired in 32,000 years. Taking into consideration the limited amount of meteoric matter available near the sun, he concluded that sunlight cannot last as at present for 300,000 years. This theory attracted little attention when promulgated by him in 1854 and was abandoned by him later. But in the same year, Helmholtz, working along the lines of the nebular hypothesis of Kant and Laplace, derived the heat of the sun from the contraction of the nebula from which the sun and planets were formed. He asserted also a further contraction of the sun, now assumed to be in progress, by which the kinetic energy obtained was converted into heat and compensated for the loss of solar heat by radiation. Accordingly, if the sun contracts 1/10,000th part of its radius each year, enough heat would be generated to supply radiation for 2,100 years. Helmholtz's computation gives 22 million years as the probable age of the sun, based on a uniform radiation and homogeneous density of that body. Later, S. P. Langley, with experimental data derived from the direct radiation of the sun, reduced this age to 18 million years. This theory immediately supplanted that of the falling meteors, which more serious reflection demonstrated could account only for the slight increase in the solar heat as compared with the energy of shrinkage. Lord Kelvin in 1862 returned to the subject, favoring a theory like that of Helmholtz's, concluding that we may accept as the lowest estimate for the sun's initial heat 10 million times a year's supply at the present rate, but 50 million or 100 million as possible in consequence of the sun's greater density in his central parts. As for the future, inhabitants of the earth cannot continue to enjoy the light and heat essential to their life for many million years longer, unless sources now unknown to us are prepared in the great storehouse of creation. Studies of the sun's heat were continued by Lord Kelvin, and in his theory he incorporated a discovery made in 1870 by J. Homer Lane, an American, which paradoxically demonstrated that within certain limits, the more heat a gaseous body loses by radiation, the hotter it will become. This theory of Helmholtz's, as modified by Kelvin, encountered a serious rival in 1882, when Sir William Siemens proposed that a rotating sun hurled by centrifugal action at the equator enormous quantities of gas into space, which returned to it again at the poles, somewhat after the manner of a regenerative furnace. Helmholtz's theory was modified in 1899 by Professor T.J.J.C., who abandoned the German scientist's hypothesis of homogeneous density for the sun and applied Lane's law, investigating minutely the more complex case of central condensation. As the result of his study, the probable age of the sun was extended from 22 million to about 32 million years. All of these researches came before the discovery of radium, and when the extraordinary properties of this new substance were known, it was stated that a bare fraction of a % of radium present in the sun would account for and make good the heat that is annually lost by radiation. Should this hypothesis hold good, an entirely new aspect is given to the problem of solar heat and to the heat of the earth. This innovation, advanced by members of the younger school of physicists, all of whom had prosecuted with vigor researches in radioactivity, did not appeal to Lord Kelvin, who maintained in 1906 that the gravitation theory was still sufficient to account for the sun's heat. No evidence has been produced of the presence of radium in the sun, although helium has been found there. As helium is obtained from radium, the existence of radium in the sun is quite probable. Sir George H. Darwin, in discussing the effect of these recent discoveries on solar age, says, "Knowing as we now do that an atom of matter is capable of containing an enormous store of energy in itself, I think we have no right to assume that the sun is incapable of liberating atomic energy to a degree at least comparable with that which it would do if made of radium. Accordingly, I see no reason for doubting the possibility of augmenting the estimate of solar heat as derived from the theory of gravitation by some such factor as 10 or 20. It is obvious, therefore, that while the contraction theory explains the origin of a vast amount of the sun's heat, yet there are other sources of internal energy which recent discoveries plainly indicate are of great importance, so that the scientist at this stage is unable to declare positively the age of the sun or to make any accurate estimate as to the probable duration of the time through which it will afford light and heat to the Earth and the other planets. Nevertheless, it seems assured that millions of years hence, how many cannot even roughly be determined, the sun will be reduced from a ball of glowing vapor to a gigantic black cinder rushing through space. Unwarmed by any central luminary, its crust will be washed by oceans of air liquefied by a cold too intense for any living creature to endure. The light of the sun is obviously more intense than any other luminant known to man. If compared with the full moon, 600,000 times as much light is received from the sun. Expressed in another way, the sun gives over 60,000 times as much illumination as a standard candle at a distance of 1 yard. But not all of the light and heat which is radiated from the sun comes to the earth. Professor Langley, in his experiments at Mount Whitney in 1881, found that a clear atmosphere would cut off 40% of the rays coming perpendicularly to the earth's surface. Gases in the atmosphere, such as carbon dioxide, cut off even a greater amount, and the general absorption is greater at the violet end than at the red. It is for this reason that high altitudes and a clear atmosphere are essential for solar investigation, and for this reason, too, that the setting sun appears red, the bluish rays being absorbed in traversing a greater amount of terrestrial atmosphere than when the sun is high in the sky. The temperature of the sun can be estimated from its brilliancy and from spectroscopic and bolometric studies. It is a common experience that a filament of an incandescent lamp emits more light and glows more brightly when the amount of current is increased. At first the filament is red, but as more current is permitted to flow it becomes yellow and finally a brilliant white. This is marked by an increase in temperature, and secondly, the temperature depends upon the brilliancy of the glow. The same analogy holds good in the case of the sun and the stars. If the wavelength of the radiation is known, and the color which emits the greatest amount of heat in the spectrum, and this can be measured by the bolometer by a simple law, it is possible to calculate the absolute temperature of a star. Then, by deducting 270 degrees from the result, its temperature in the ordinary centigrade degrees is obtained. Thus, in the case of the sun, the maximum heat radiation occurs in the greenish-yellow light, which gives a temperature for the rotating disk of the sun of about 5,000 degrees centigrade or 9,000 degrees Fahrenheit. The atmospheric absorption already referred to serves to cut down the intensity of the radiation, so that, taking this and other amounts into consideration, the temperature of the sun's disk can be estimated at about 6,200 degrees centigrade. Similar investigation in the case of Sirius and Vega, which are white or younger stars, give a temperature about 1,000 degrees Celsius higher than that of the sun, while the red star, Betelgeuse, which is a declining star, older than the sun, has a temperature some 2,500 degrees centigrade less. The temperature of the sun furnishes different results, depending on the manner in which the problem is attacked. Arrhenius, in his work on Worlds in the Making, summarizes recent work and states that, from the intensity of the radiation, Christensen and afterward Warburg calculated a temperature of about 6,000 degrees centigrade. Wilson and Gray found for the center of the sun 6,200 degrees, which they afterward corrected into 8,000 degrees. Owing to the absorption of light by the terrestrial and the solar atmospheres, two low values are always found. That applies to a still greater extent to any estimate based upon the determination of that wavelength for which the heat emission from the solar spectrum is maximum. Le Chatelier compared the intensity of sunlight filtered through red glass with the intensities of light from several terrestrial sources of fairly well-known temperatures treated in the same way. These estimates yielded to him a solar temperature of 7,600 degrees centigrade. Most scientists accept an absolute temperature of 6,500 degrees, corresponding with about 6,200 degrees centigrade. That is what is known as the effective temperature of the sun. If the solar rays were not partially absorbed, this temperature would correspond with that of the clouds of the photosphere. Since red light is little absorbed, Comparatively, Le Chatelier's value of 7,600 degrees centigrade and the almost equal value of Wilson and Gray of 8,000 degrees centigrade should represent approximately the average temperature of the outer portions of the clouds of the photosphere. The higher temperature of the faculae is evident from their greater light intensity, which, however, may be partly due to their greater height. Carrington and Hodgson saw, on September 1, 1859, two faculae break out from the edge of a sunspot. Their splendor was 5 or 6 times greater than that of the surrounding parts of the photosphere. That would correspond with a temperature of about 10,000 or 12,000 degrees centigrade. The deeper parts of the sun which broke out on these occasions evidently have a higher temperature, and this is not unnatural, since the sun is losing heat by radiation from its outer portions. At all events, the Earth receives a large amount of energy in the form of light and heat, which amounts to 3 horsepower for every square yard of space perpendicular to the sun's rays. And while this really is not readily available for mechanical purposes, yet solar engines have been constructed in which this energy has been transformed into power. While the energy of the sun is not, generally speaking, available for mechanical purposes, yet indirectly the heat received by the Earth has made possible plant and animal life, on which depends the source of all energy. The transmission of the sun's heat to the Earth is one of the important problems of present-day physics and meteorology, inasmuch as the amount of radiation or heat emitted by the sun, spoken of by physics as the solar constant, and the relation of this radiation to terrestrial temperature, as well as the study of the radiation of different parts of the sun's disks, are all topics of fundamental importance. The solar constant is measured outside of the Earth's atmosphere at mean solar distance, and the intensity of radiation is employed for a unit which, when fully absorbed for 1 minute over a square centimeter of area placed at right angles to the ray, would produce sufficient heat to raise the temperature of a gram of water 1 degree centigrade. If once the original quantity and kind of heat emitted by the sun be known, its effect on the constituents of the atmosphere on its journey to the Earth, how much of it reaches the soil, how through the change of the atmosphere it maintains the surface temperature of our globe, and finally how in diminished quantity, or altered kind, it is returned to outer space, it would be possible to predict nearly all of the phenomena of the weather. Thus, it has been known that when there is a small decrease in the solar radiation, there follows a marked and general decline in temperature. So that, knowing the variation of radiation, it should be possible to predict changes in climate. These data are secured by measuring the total intensity of the radiation as it arrives at the Earth's surface with the pyrheliometer, or thermometer with blackened bulb, carefully protected from all other influences except the direct rays of the sun. And in the second place, by measuring the heat or energy in different parts of the solar spectrum with the spectrobolometer. The absorption of the atmosphere nearer the Earth for different areas requires measurements to be made at several stations. For at Washington, near the sea level, the intensity of radiation actually observed is only about 3/4 as great as that observed in the clear atmosphere of Mount Wilson at a height of 6,000 feet. Recent observations made at Mount Wilson and Washington by Mr. Abbott of the Astrophysical Laboratory of the Smithsonian Institution indicate that heat sent out to the Earth from the sun in the course of a year is capable of melting an ice shell 114 feet thick over the whole surface of the Earth. The solar radiation is not a constant quantity, but varies with the decrease in solar distance, the changes occurring from month to month and from year to year. The variation is due to the changes in the source of radiation rather than to the effects of our atmosphere or external causes. The distance and position of the sun as regards the other members of the solar system has been considered in a previous chapter. It is known that its apparent diameter is 32 arc minutes, 4 arc seconds, which corresponds with 866,500 miles, or 109.5 times the diameter of the Earth. This would give it an area 11,950 times that of the Earth and a volume 1,306,500 times greater. The actual mass of the Sun is 332,000 times that of the Earth, but its average density is only about a quarter as great, so that the Sun, which has a density of 1.41 as compared with water, is 4 times as large as it would have to be if its density were the same as that of the Earth. Taking into consideration this lightness as well as the high temperatures prevailing in the Sun, one is forced to the conclusion that the body of the Sun must be in a gaseous state. The conditions under which the gases are found must be quite different from those with which we are acquainted on the Earth. Gravity at the surface of the Sun exceeds by more than 27 times gravity on the Earth. The motion of the Sun as regards the other stars in the heavens has been treated elsewhere, but it is proper here to refer to its rotation on its axis from west to east, which takes place in a period of about 25 days and is apparent from the motion of the sunspots, though it can also be detected by directing a spectroscope toward the edges of the limb and noting by Doppler's principle how one side is approaching the observer and the other is retreating. The time of rotation is not the same for all parts of the disk, but depends upon the position of the spots selected. Those nearest the equator show the most rapid rotation. End of section 14.
Section 15 of the Science History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Larry Wilson. The Science History of the Universe, Volume 1, edited by Francis Rolt Wheeler. Astronomy. Chapter 11, Mercury. Ancient records make no mention of the discovery of Mercury, yet the existence of the planet was surely known even in the days of Nineveh, when a chief astronomer directly refers to the planet in a report which he made to King Assurbanipal of Assyria. The planet is occasionally mentioned in early and medieval astronomical literature. It is stated that Copernicus regretted that he had never been able to observe it properly in the high altitude of Frauenburg. That the planet should have been overlooked by the ancients is not strange when it is considered that it is never visible in the higher altitudes except occasionally near the horizon just after sunset or before sunrise. In the clear sky over an eastern desert, the primeval astronomer doubtless saw this bright star in that part of the horizon where the setting sun was still shedding its beams. Its luster diminishes as the planet draws near the horizon at sunset, until finally it sets so soon after the sun that it is invisible. Years may elapse before a similar opportunity is afforded. If a similar phenomenon took place at sunrise, the primitive astronomer might have inferred that Venus and Mercury were identical, especially as a long series of observations would establish the fact that one of these bodies was never seen until the other had disappeared. Accordingly, some of the ancient astronomers assumed that there was but one morning and evening star. But as records accumulated, it was recognized that there were two bodies which might serve as morning and evening stars. A certain regularity in the recurrence of each planet was noted, and it was possible to make predictions of accuracy as to the time when either could be seen after sunset or before sunrise. While by the time of Plato it was known that Venus and Mercury performed their revolutions in approximately the same time, it was recognized that Mercury's period was different and more rapid than that of other planets. An older tradition, attributed to the Egyptians, stated that both planets revolved around the sun. Ptolemy states that they could be regarded as oscillating to and fro on each side of the sun. That the ancient astronomers might well have been confused by the appearance of Mercury as morning and evening star follows from a consideration of the planet's position and motion relatively to the sun and the earth. The consideration, moreover, applies to Venus as well. Quoting C. G. Dolmage's Astronomy of Today, when furthest from us, Mercury is at the other side of the sun, and cannot then be seen owing to the blaze of light. As it continues its journey, it passes to the left of the sun, and is then sufficiently away from the glare to be plainly seen. It next draws in again toward the sun, and is once more lost to view in the blaze at that time of its passing nearest to us. Then it gradually comes out to view on the right hand, separates from the sun up to a certain distance as before, and again recedes beyond the sun, and is for the time being once more lost to view. To these various positions technical names are given. When the inferior planet is on the far side of the sun from us, it is said to be in superior conjunction. When it has drawn as far as it can to the left hand, and is then as east as possible of the sun, it is said to be at its greatest eastern elongation. Again, when it is passing nearest to us, it is said to be in inferior conjunction. And finally, when it has drawn as far as it can to the right hand, it is spoken of as being at its greatest western elongation. The continual variation in the distance of the inferior planets, Venus and Mercury, from the Earth during their revolution around the sun will of course be productive of great alterations in apparent size, which no doubt also had its effect in bewildering the ancients. At superior conjunction, being then farthest away, Mercury ought to show the smallest disk, while at inferior conjunction, being the nearest, it should appear much larger. When at greatest elongation, whether eastern or western, it should naturally present an appearance midway in size between the two. From these considerations, it would seem that the best time for studying the surface of Venus or Mercury is at inferior conjunction, or when the planet is nearest to the Earth. But that this is not the case will at once appear if it is considered that the sun's light is then falling upon the side most distant, leaving the proximate side unilluminated. In superior conjunction, on the other hand, the light falls upon the side of the planet facing the Earth. But the disk is then so small, and the view besides is so dazzled by the proximity of the sun, that observations are of little avail. In the elongations, however, the sunlight comes from the side, and so we see one half of the planet lit up, the right half at eastern elongation and the left half at western elongation. Piecing together the results given at these more favorable views, it is possible bit by bit to gather some small knowledge concerning the surface of Mercury or Venus. Consequently, it will be seen that the inferior planets show various phases comparable with the waxing and waning of the moon in its monthly round. Superior conjunction is, in fact, similar to full moon, and inferior conjunction to new moon, while the eastern and western elongations may be compared respectively with the moon's first and last quarters. When these phases were first seen by the early telescopic observers, the Copernican theory was felt to be immeasurably strengthened, for it had been pointed out that if this system were correct, the planets Venus and Mercury, were it possible to see them more distinctly, would of necessity present phases when viewed from the Earth. The apparent swing of an inferior planet from side to side of the sun, at one time on the east side, then passing into and lost in the sun's rays, to appear once more on the west side, is the explanation of what is meant when one speaks of an evening star or a morning star. Mercury of Venus is called an evening star when it is at its eastern elongation, that is to say, on the left hand of the sun. For being then on the eastern side, it will set after the sun sets, as both sink in their turn below the western horizon at the close of day. Similarly, when either planet is at its western elongation, that is to say, to the right hand of the sun, it will precede him, and so will rise above the eastern horizon before the sun, receiving therefore the designation of morning star. Mercury's motions were early studied. With the planet was associated the first of the remarkable astronomical predictions that now have become almost commonplace, so carefully are they worked out by astronomers. Kepler, from his studies of the motions of the planet, was the first to realize that if the orbit of Mercury, which, as has been seen, lies within that of the Earth, and thus nearer the sun, were exactly circular, and in the plane of the ecliptic, a transit of Mercury across the sun's disk would occur once in each synodical revolution, or period between two successive conjunctions of the planet with the Sun as seen from the Earth. The epoch of the transit could be calculated very easily. But Mercury's orbit is inclined 7 degrees to the ecliptic, and is very eccentric, for which reason his calculations were only approximately correct. It was in 1627 that Kepler predicted transits of both Mercury and Venus across the Sun, and assigned the date of November 7th for the former. Gassendi, to whom was entrusted the task of proving Kepler's prophecy, began his observation on the 5th of November, watching the image of the Sun formed by a lens on a white screen from light emitted through a hole in a dark room. But Kepler was not in error by as much as that. Only 5 hours after the time assigned did the transit actually begin. Thus was commenced a series of observations of the time when Mercury crosses the great central luminary of this system. These transits are by no means rare, for 13 of them were observed in the 19th century. They afford opportunity for observation which enables the movements of the planet to be calculated with accuracy. After the transits of 1661 and 1677, Lahire constructed new tables of Mercury and predicted a transit on May 5, 1707. The calculation was in error by nearly a day. After the transit of May 1753 had been observed several hours later than Lahire's, and as much earlier than Halley's prediction, Lalande constructed new tables and predicted the transit of 1786, which actually took place 53 minutes later than the time announced by Lalande and about as much earlier than the time computed by Halley's tables. Lalande then corrected his tables and predicted the transits of 1789, 1799, and 1802 with a fair approach to accuracy. The tables compiled by Lindenau in 1813 still left much to be desired. The problem of Mercury's motion was in this condition when it was attacked by Leverrier, who was under no illusion in regard to its difficulty. Leverrier did not succeed in overcoming the difficulty until 1859. As a result of his work, supplemented by that of later investigators, astronomers are now in possession of at least fairly accurate information on the subject of the planet's orbital phenomena. It is known, for example, that Mercury is the swiftest in its movements of all the planets. With the exception of some of the satellites, it has an orbit that departs most from the circular form. In other words, an orbit marked not only by the greatest eccentricity, but also by the greatest inclination of all planetary orbits to the ecliptic. This eccentricity of the orbit is such that the Sun is 7.5 million miles out of its center, while the actual distance of the planet from the Sun ranges from about 29 million miles to 53 million, or a mean distance of about 36 million of miles. The velocity varies from 35 miles a second when the planet is at perihelion, or nearest the Sun, at the pointed end of its oval course, to about 33 miles a second at aphelion. To explain the perturbations in Mercury's motion, Abbe Moreau has recently advanced the following hypothesis. The Sun is unquestionably surrounded by matter, which gives rise to the observed phenomena of the corona. Photographs made during the eclipse of 1905 showed an outer corona extending to a hitherto unsuspected distance from the Sun. This outer corona is ellipsoidal, and its major axis is very nearly coincident with that of the zodiacal light. This region, then, is filled with a resisting medium, composed of matter which is gradually falling in toward the Sun. The mechanism of this fall, or contraction, is very complex, and as we have no idea of the identity of the matter, it is difficult to calculate its changes in form. The resistance which the medium opposes to a moving body is likewise difficult to estimate, but we know from the observed acceleration of comets that this resistance is by no means negligible. At the epochs of maximum coronal development, this resisting medium may easily extend to the orbit of Mercury. Hence, that planet, in its revolution around the Sun, must traverse masses of rarefied gas and swarms of minute particles by which its course is modified. We are far from knowing the quantitative effect of the resisting medium, and much study of the corona will be required to complete the solution of this interesting problem. Because of the lack of surface markings, the rotation periods are very uncertain. Recently, Professor Macquart in France has deduced a rotation of 24 hours, 8 minutes. G. Schiaparelli has put forward the view that both Venus and Mercury rotate in a time equal to the individual period of revolution around the Sun, and thus always turn the same face toward the Sun. Such a motion, which is analogous to that of the Moon around the Earth, could be easily explained as the result of tidal action at some past time when the planets were, to a great extent, fluid. This may be true, as Mercury is one of the planets which has no moon, and consequently will be influenced directly and solely by the Sun insofar as tidal phenomena are concerned. These tidal effects must be especially severe on account of the proximity of Mercury to the Sun. Because of this lack of a satellite, the mass of the planet is very difficult to determine. At various times, Laplace, Encke, and Leverrier have given values of 1/9 to 1/30 of the Earth's mass. The first convenient opportunity of placing this planet in a gravitational balance of determining its mass was presented in August 1835, when Encke's comet, in the course of its eccentric path through the solar system, penetrated within the orbit of Mercury at its perihelion. The attractive power of the planet produced only a slight deviation from the regular course of the comet, sufficient, however, to show that the value previously assumed for Mercury's mass was nearly twice too large. At the same time, the calculations made from these data have not removed the uncertainty that still prevails upon this point. Simon Newcomb decided on a value of about 1/21st of that of the Earth, while William Harkness made it 1/25th. Beyond its motion, comparative little is known of Mercury. The spectroscope seems to indicate that the atmosphere of Mercury contains water vapor, just as does the Earth. But the studies of Professor Lowell at Flagstaff, Arizona, do not show any signs of clouds or obscurations, and there are no indications of any atmospheric envelope. In fact, the surface of Mercury has been termed colorless, a geography in black and white. The first student of the surface of Mercury was Johann Hieronymus Schroter, 1745 to 1816, who, as will be seen, was a pioneer in the study of the topography of the Moon. In April 1792, Schroter concluded from the gradual degradation of light on its brightly illuminated disk that Mercury possessed a tolerably dense atmosphere. During the transit of May 7, 1799, he was struck with the appearance of a ring of softened luminosity circling the planet to a height of 3 minutes and about a quarter of its own diameter. Referring to this ring as softened luminosity, Agnes Clerk writes in her History of Astronomy, "Although a mere thought in texture, it remained persistently visible both with the 7-foot and 13-foot reflectors, armed with powers up to 288. A similar appendage had been noticed by Desplantades of Montpellier, November 11, 1736, and again in 1786 and 1789 by Prosperin and Lagergus. But Herschel, on November 9, 1802, saw the preceding limb of the planet projected on the Sun cut the luminous solar clouds with the most perfect sharpness. The presence, however, of a halo was unmistakable in 1832, when Professor Moll of Utrecht described it as a nebulous ring of a darker tinge approaching to a violet color. Again, to Sir William Huggins and Stone on November 5, 1868, it showed as lucid and most distinct. No change in the color of the glasses used or the powers applied could get rid of it, and it lasted throughout the transit. It was next seen by Christie and Duncan at Greenwich, May 6, 1878, and with much precision of detail by Trouvelot at Cambridge, Massachusetts. Professor Holden, on the other hand, noted at Hastings-on-Hudson the total absence of all anomalous appearances, nor could any vestige of them be seen by Bernard at Lick on November 10, 1894. Various effects of irradiation and diffraction were, however, observed by Lowell and W. H. Pickering at Flagstaff, and Davidson was favored at San Francisco with a glimpse of the historic aureola, as well as of a central whitish spot which often accompanies it. That both are somehow of optical production can scarcely be doubted. The planet's physical condition presents many problems, and the spectroscope affords little information as to its constitution. As it shines only by reflected light from the sun, its spectrum is but a fine echo of the Fraunhofer lines. An atmosphere like that of the earth was suspected, however, by H. C. Vogel in 1871 from his spectroscopic studies, though on the very slightest grounds. Later observations made at the Potsdam Observatory by Miller confirm this conclusion and demonstrate that Mercury has a rough rind of dusky rock, which absorbs all but 17% of the direct light radiated upon it by the nearby sun. This would seem to show the utter absence of any appreciable Mercurian atmosphere. The probable lack of atmosphere is also shown by the circumstance that when Mercury is just about to transit the face of the sun, no ring of diffused light is seen to encircle its disk, as would be the case if it possessed an atmosphere. According to the Belgian astronomer Stroobant, the linear diameter of Mercury expressed as a fraction of the Earth's is 0.350, instead of the previously accepted 0.373. The radius 2,232 kilometers, 1,386.7 miles, and the volume compared with that of Earth is 0.042. End of section 15. Section 16 of the Science History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Larry Wilson. The Science History of the Universe, Volume 1, edited by Francis Rolt Wheeler, Astronomy. Chapter 12, Part 1. For all time, Venus has been known as evening and morning star. By the ancients, it was supposed to be two separate bodies, which were named Phosphorus, Lucifer, or morning star, and Hesperus, Vesper, or evening star. For Pythagoras in the 6th century B.C. has claimed the honor of discovering the identity of the two stars, but it was probable that he restated the views of Eastern astronomers. As the most brilliant star in the heavens, Venus is certainly the one that has always been most observed. Glittering in the sky like a clear diamond, its pure white light, which on a night where there is no moon is strong enough to cast a shadow, naturally would impress all whose lives are spent out of doors. Hence Venus has always figured in literature as the shepherd's star. Homer speaks of the planet as Callistus, the beautiful, and as a type of beauty, its worship figures in all mythologies. At a time when the planets were personified as gods and goddesses, it is easy to understand why this star was selected to typify love. Not only on account of its splendor in the evening sky, but for other phenomena, Venus is familiar in history and literature. The historian Varro, 116-28 B.C., states that Aeneas, on his voyage from Troy to Italy, saw this planet constantly above the horizon, and the same historian is quoted by St. Augustine as speaking of a change in the color and brilliancy of Venus. In 1716, the visibility of Venus in full daylight was hailed as a marvel by the people of London, and in 1750 its appearance at noon aroused general astonishment in Paris. Again, in 1797, when Napoleon returned to Paris from his conquest of Italy, he found the attention of the populace divided between his reappearance and a similar striking midday phenomenon. In fact, Bonaparte always associated this star with his fortunes, and one evening, while engaged in viewing the starry heavens, pointing to the planet, said to Prince Talleyrand, "Do you see? That is my star. So long as it shines, I will have no doubt of success." In more recent times, many brilliant appearances of the planet have been observed, the interval between periods of greatest visibility amounting to 8 years. At one of these, in April 1905, at Cherbourg, Venus appeared as a bright meteor of appreciable size and full form, an effect which was due partly to the formation of a halo. According to the Ptolemaic theory, Venus was always between the Earth and the supposed orbit of the Sun. Hence it was possible that, at the most, but half of its illuminated surface could be visible to the Earth. When Galileo, with his telescope in 1610, made the striking discovery that Venus appeared in various phases, just as the Moon, exhibiting the gibbous as well as the crescent phase, it was a strong and almost the last argument necessary to establish beyond question the Copernican theory that the planets revolve around the Sun. Were Venus as large as Jupiter, for example, the phases would readily be discerned by the unaided eye. Indeed, Sir Robert Ball has wondered what would have been the effect on the history of astronomy had Venus been of the size of Jupiter, so that its crescent form could have been seen without a telescope. Then the elementary truth would have been apparent that Venus was a dark body revolving around the Sun. The analogy between it and our Earth would have been at once perceived, and the theory of Copernicus long since might have been established. The mean distance of Venus from the Sun is 67,200,000 miles. With the exception of the Moon and an occasional comet, no other heavenly body comes so near the Earth at any time. The orbit is marked by the smallest eccentricity in the planetary system, and is therefore more nearly circular than that of any other planet. The planet's greatest and least distance from the Sun vary from the mean only by about 470,000 miles each way. Venus is the nearest planet to the Earth, as there is only 26 million miles between the orbits of the two at inferior conjunction or their nearest approach. Yet Venus is not as well known as Mars, since when Venus passes nearest the Earth, it is then between it and the Sun, so that the hemisphere which is illuminated is not visible to the Earth. The appearance of Venus in the sky as the evening and the morning star was no less impressive to the ancients than the beautiful character of the star itself. It is as familiar now as it was to the shepherds of old that when Venus disengages himself in the evening from the rays of the setting sun, it departs from the Sun a little more every night, increasing its brilliancy until a certain distance in the east is reached, appearing, like the Moon, to travel toward the left of the observer. At the end of a few months it has removed itself from the Sun to an angular distance that may amount to as much as 48, at which time the planet sets more than 3 hours after the Sun. After shining for some months, little by little the planet begins to return toward the Sun, receding more and more from the Earth, then passing behind the central luminary, and thus ceasing to be the evening star. After an interval, a new star is seen in the early morning, to precede the rising of the Sun, advancing by imperceptible degrees every day, and eclipsing likewise all the bodies of the heavens by its dazzling light. At this time it proceeds toward the west, that is, toward the observer's right hand, and we have now the morning star. After having preceded the rising of the Sun by 3 hours, Venus resumes its course anew toward the Sun, and again is lost in the glare of day. It is then passing between the sun and the earth, and is at its greatest proximity to the earth. Sometimes it passes just in front of the sun, as it did in 1874 and 1882, which phenomenon is known as a transit. As it happens but twice in a century, a transit is an occurrence of considerable importance to astronomers. These transits are valuable for the easy determination of the position of the planet, for the investigation of its atmosphere, and for the determination of the solar parallax by comparing the amount of apparent displacement in the planet's path across the solar disk when the transit is observed at widely separated stations on the Earth's surface. These transits occur in June and December, taking place in cycles whose intervals are 8, 105.5, 8, 121.5 years. They have occurred on the following dates: December 7th, 1631, December 24th, 1639, June 5th, 1761, June 3rd, 1769, December 9th, 1874, December 6th, 1882, and will occur again on June 8th, 2004, and June 6th, 2012. The first observed transit, namely that of 1639, was watched in England by two persons, Jeremiah Horrocks and a friend William Crabtree, whom Horrocks had forewarned of its occurrence. That the transit was observed at all was due entirely to the remarkable ability of Horrocks. According to the calculations of Kepler, no transit could take place that year, 1639, as the planet would just pass clear of the lower edge of the sun. Horrocks, however, worked the question out for himself and came to the conclusion that the planet would actually traverse the lower portion of the sun's disk. The event proved him to be right. Horrocks, who was said to have been a veritable prodigy of astronomical skill, unfortunately died about 2 years after the celebrated transit in his 22nd year. The transits of Venus next observed in 1761 and 1769 were taken advantage of by Edmund Halley to suggest a means of ascertaining the distance of the sun. The idea had originated in rather vague form with Kepler, but was suggested more definitely by James Gregory in 1663. After Halley had observed the transit of Mercury in 1677, he realized the advantages of the method and published several papers urging preparations for observing the transit. He pointed out, says Berry, treating of this point in his Short History of Astronomy, that the desired result could be deduced from a comparison of the durations of the transit of Venus as seen from different stations of the earth, i.e., of the intervals between the first appearance of Venus on the sun's disk and the final disappearance as seen at 2 or more different stations. He estimated, moreover, that this interval of time, which would be several hours in length, could be measured with an error of only about 2 seconds, and that in consequence the method might be relied upon to give the distance of the sun to about 1/500th part of its true value. As the current estimates of the sun's distance differed among one another by 20 or 30%, the new method, expounded with Halley's customary lucidity, was an enthusiasm not unnaturally stimulated astronomers to take great trouble to carry out Halley's recommendations. The results, however, were by no means equal to Halley's expectations. Immense trouble was taken by governments, academies, and private persons in arranging for the observation of the transits of 1761 and 1769. For the former, observing parties were sent as far as Tobolsk, St. Helena, the Cape of Good Hope, and India, while observations were also made by astronomers at Greenwich, Paris, Vienna, Uppsala, and elsewhere in Europe. The next following transit was observed on an even larger scale, the stations selected ranging from Siberia to California, from the Varanger Fjord to Otaheite, where no less famous a person than Captain Cook was placed, and from Hudson's Bay to Madras. The expeditions organized on this occasion by the American Philosophical Society may be regarded as the first of the contributions made by America to the science which has since owed so much to her, while the Empress Catherine of Russia bore witness to the newly acquired civilization of her country by establishing a number of observing stations on the soil of her empire. A variety of causes prevented the moments of contact between the disks of Venus and the Sun from being observed with the precision that had been hoped. The values of the parallax of the Sun deduced from the earlier of the two transits ranged between 8 minutes and 10 minutes, while those obtained in 1769, though much more consistent, still varied between 8 minutes and 9 minutes, corresponding with a variation of about 10 million miles in the distance of the Sun. The whole set of observations was subsequently very elaborately discussed in 1822 to 1824, and again in 1835 by Johann Franz Encke, who deduced a parallax of 8 minutes 57 seconds, corresponding with a distance of 95,370,000 miles, a number which long remained classical. The uncertainty of the data is shown by the fact that other equally competent astronomers have deduced from the observations of 1769 parallaxes of 8 minutes 0.8 and 8 minutes 0.9. End of section 16. Section 17 of the Science History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Larry Wilson. The Science History of the Universe, Volume 1, edited by Francis Rolt Wheeler, Astronomy. Chapter 12, Part 2. The transits of Venus in 1874 and 1882 were memorable as the first in which photographic methods and the heliometer were applied, in addition to the older methods of time observation to measure the occasion of contact. The older methods left unavailable the remainder of the transit, but the heliometer made it possible to ascertain the planet's apparent position upon the Sun's disk at any time with great precision. In the transit of 1874, the most elaborate photographic measures ever undertaken until this time were carried out in the United States where conditions were most favorable. A continuous succession of photographs was made as the planet traveled across the Sun's disk, and various systems of reference enabled its position to be identified with great accuracy at any part of the transit. Yet results were hardly more valuable than those obtained by other methods. Hence, in 1882, the American observers modified their apparatus considerably from previous practice by employing the photographic plate and using the heliostat to reflect the Sun's rays through a telescope lens 5 inches in diameter and of 40-foot focal length. Doubtless better results could be obtained today with modern solar photographic equipment and dry plates. No great advances were recorded as the result of the numerous expeditions during these two transits. Elaborate expeditions were equipped particularly for the second of the two transits, and the observations which were voluminous were thoroughly and systematically discussed. The results were a somewhat larger value of the solar parallax, amounting to 8 minutes 0.857, or rather less than 93 million miles, as obtained by Newcomb after combining the heliometer with photographic measurements. As all measurements of this kind seem to be affected by some constant systematic error, it is the consensus of opinion among astronomers that other methods are more to be trusted in determining the solar parallax than those based on the transits of Venus. The great brilliancy of Venus is due to its relatively small distance from the Sun and the Earth and to its great reflecting power. The albedo of Venus, or the ratio of reflected to incident light, is 0.76. In other words, the planet reflects 3/4 of the light that falls upon it from the sun, a proportion which is little exceeded by freshly fallen snow. This indicates that Venus is surrounded by a dense and cloudy atmosphere. Similar indications are given by the spectroscope, pointing to the existence of an atmosphere containing water vapor and generally similar to our own, but denser. This atmosphere of Venus, owing to its great refractive power, sometimes appears as a luminous ring in transits of the planet. From observations made at the transit of 1882, it has been computed that the density of the atmosphere of Venus is 1.8 that of the Earth's atmosphere, which produces a refractive displacement of 33 minutes. According to Medler's calculations, the atmosphere of Venus is 1.7 times as dense as that of the Earth. Many astronomers believe, therefore, that Venus is surrounded by a dense atmosphere into which the sun's rays do not penetrate to a depth sufficient to cause much loss by absorption, probably because they are reflected by opaque clouds. From this it would follow that the markings which have been observed on the disk of Venus through the telescope for centuries may be purely atmospheric. As the displacement of the surface markings of a planet when viewed through a telescope furnish the basis for estimates of the period of rotation, it may be that calculations so made are without justification. These markings of Venus are altogether different from those of any other planet. They are faint, indistinct, and apparently variable, for the drawings of Venus made by different observers before the advent of photography are very unlike. The first astronomer to observe any markings on Venus was Domenico Cassini, who discovered a bright spot in 1666. In the following year, he discovered a second spot from which he deduced a period rotation of about 24 hours, an estimate which was reduced to 23 hours and 22 minutes in Jacques Cassini's revision of his father's work. On the other hand, Bianchini, who studied the planet in 1726 and 1727, deduced from his observations a period of rotation equal to 24 days and 8 hours. Thus began the long and violent controversy in regard to the rotation of Venus. From more than 10,000 observations made between 1830 and 1841, De Vico computed a mean value of 23 hours, 21 minutes, and 23.93 seconds for the period of rotation of Venus. This value, furthermore, agrees very closely with the period of 23 hours deduced by Schroter from observations of the deformation of the horns of Venus 1788, 1793, and it has consequently been adopted in most treatises on astronomy. But in 1890, however, belief in the short period was shaken by Schiaparelli's discoveries. Before this, Schiaparelli had made this surprising announcement that the period of rotation of Mercury was equal to the period of its revolution about the sun, and he now asserted that the same law governed the motions of Venus, a statement based on observations made in the winter of 1877-78, which showed that the bright spots then visible never varied their positions with respect to the terminator, or boundary line between the planet and its shadow. Observations made in 1895 gave additional support to the view that Venus rotates on her axis in the period of her revolution about the sun, 225 days, and consequently always turns the same hemisphere toward the sun, just as the moon always presents the same face to the earth. This theory, which on its announcement rested solely on Schiaparelli's authority, soon obtained strong independent support. It has apparently been completely confirmed by the observations made by Lowell at Flagstaff, Arizona in 1895-6. Lowell saw markings that have been seen by no other astronomer before or since, but the most surprising thing about his discoveries is that he saw no spots, but only bands or lines bearing a superficial resemblance to the canals of Mars. The whole configuration remained unchanged for hours, which could not be the case if the period rotation were only 24 hours. Furthermore, the markings remained fixed relatively to the terminator. Lowell denies the existence of clouds on Venus, although he finds in certain phenomena of twilight evidence of the presence of a very dense atmosphere. Many astronomers have refused to accept the conclusions of Schiaparelli, Perrotin, and Lowell, and have adhered to the theory of a short period of rotation. Schiaparelli's first announcement was vigorously disputed soon after its publication by the French astronomer Trouvelot. During his residence at Cambridge, Massachusetts, from 1875 to 1882, Trouvelot pointed out 17 changes in the markings which Schiaparelli regarded as fixed. Trouvelot regarded the bright spots on the limb of the planet as very high mountains rising above the atmosphere. The observed changes in the appearance of the horns of the crescent planet have also been ascribed to mountains. In the 18th century, Schroter announced the discovery of several mountains on Venus. In 1789, the southern horn of the crescent appeared blunted, and near it on the dark disk of the planet shone a bright peak, the height of which was estimated by Schroter as 117,000 feet, or 22 miles. Trouvelot deduced from his own observations a period of rotation of about 24 hours. It is very remarkable that two such experienced and trustworthy observers as Schiaparelli and Trouvelot could be led to such widely differing results from their frequent observations of the same object during the same period. It may be regarded as certain that the problem of the rotation of Venus cannot be solved by observing markings, which is not surprising if they are purely atmospheric phenomena. Sir William Herschel, who has justly been called the greatest observer of all time, doubted the reality of the markings of Venus and regarded them as atmospheric phenomena. But this view was not shared by any of his contemporaries. Beer and Mädler, who were also most excellent observers, studied Venus repeatedly in 1831 and later years, but they rarely, if ever, saw anything that deserved the name of a marking. Attempts have been made to solve the interesting and difficult problem of the rotation of Venus with the aid of the spectroscope, but these attempts have also failed to give a positive result. The effort was first made by the Russian spectroscopist Jelopolsky at Pulkowa Observatory. The spectrophotographic measurements, which were begun in 1900, indicated a short period of rotation. Although Jelopolsky did not regard the correctness of the result as assured, his authority led to the belief that the spectroscope had decided the question in favor of the short period. Then Lowell, who had deduced a period of 225 days from telescopic observations, sought confirmation for this value by the spectroscopic method. He first tested his new and delicate apparatus and method by applying them to Mars, and obtained for that planet a period of rotation of 25 hours and 35 minutes, which agrees fairly well with the known period 24 hours and 37 minutes. For Venus, Lowell's spectrophotographs give a rotational velocity of from 5 to 8 meters, 16.4 to 26.2 feet per second, which corresponds with a long period of rotation, though one much shorter than 225 days, for which the equatorial velocity would be about 2 meters, 6.56 feet per second. Neither of the results obtained at Pulkowa and at Flagstaff has yet been confirmed elsewhere. The spectroscopic method is too difficult to be attempted except by a particularly well-equipped and favorably situated observatory. The theory of slow rotation receives powerful support from certain arguments advanced by the distinguished English astronomer Sir George H. Darwin. The rotational velocity of every planet must be gradually diminished by tidal friction among its parts. In this way, the period of the Moon's rotation has been made equal to the period of her rotation about the Earth, and the rotational periods of Mercury and Venus may have been similarly lengthened to equality with their periods of revolution about the Sun, which exerts a far greater tidal action upon these inferior planets than upon the Earth. If Venus has already reached this stage, all the water on the planet must be accumulated in the form of ice on the dark and intensely cold hemisphere. Hence, as Antoniadi has pointed out, the presence of clouds and water vapor on the illuminated hemisphere casts grave doubt on the correctness of Schiaparelli's theory. The presence of clouds in the atmosphere of Venus is denied only by Lowell, who saw the peculiar canal-like markings distinctly whenever terrestrial atmospheric conditions permitted. No trace of markings, by the way, was seen by Hansky and Stefanik, who studied the planet in the summer of 1907 at the Mont Blanc Observatory, which is more elevated than Flagstaff, under very favorable atmospheric conditions, and deduced a period of rotation slightly less than 24 hours. So the problem of the rotation of Venus is still unsolved, although a majority of astronomers appear to share the view of Schiaparelli and Lowell. The hope that it can be solved by observing markings has proved illusory, and there is good reason to believe that the spectroscope will ultimately furnish the solution. Venus, in size, is almost identical with the Earth. Its diameter, expressed in miles, is 7,800, as compared with 7,920 for the Earth. Its circumference consequently amounts to 23,400 miles, as compared with 25,000 miles that of the Earth. The period of revolution around the Sun is 225 days. For many years, observers have been looking for satellites of Venus. Fontana, 1645, Cassini, 1672 and 1686, and Montaigne, 1761, among others, imagined that they had made such a discovery, but these have for many years been considered optical illusions. End of section 17.
Section 18 of the Science History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Pamela Nagami. The Science History of the Universe, Volume 1, edited by Francis Rolt Wheeler. Astronomy. Chapter 13, Part 1. The Earth. The conception of the Earth formulated by the ancients assumed it to be a flat disk floating on water, which idea persisted in some form or other despite various phenomena clearly impossible of explanation upon such a hypothesis. After some more or less vague speculation on the shape of the Earth by Thales, circa 640 to circa 546 BC, a clear and rational idea was advanced by Pythagoras, who flourished in the 6th century BC and taught that the Earth, in common with the heavenly bodies, was a sphere, and that it received no support at the center of the universe. The idea of the sphericity of the Earth was doubtless derived by analogy from the appearance of the moon. The theory became an established part of Greek science and philosophy, and consequently has continued to the present day, anticipating by some 2,000 years the acceptance of the belief in the Earth's rotation. In fact, the spherical form of the Earth figured prominently in Greek astronomy, and the division of the Earth into zones and the idea of poles was promulgated by the Alexandrian philosophers and even before their time. Indeed, not only did they realize the shape of the Earth, but also its size. Eratosthenes, 276 to 195 or 196 BC, whom we have already mentioned in our chapter on pre-telescopic work, made one of the first scientific measurements of the Earth, obtaining a result which must be considered the first good geodetic measurement. He found, from the application of simple geometry, that the angular distance of the Earth's surface between Alexandria and Cyrene must be 1/50th of the circumference of the Earth. Posidonius, who was born about the end of the life of Hipparchus, made a new measurement of the circumference of the Earth, much after the fashion of Eratosthenes, but reached a value too small. One of the crucial arguments for the sphericity of the Earth is that when a ship sails away, the hull first disappears from view while the masts are visible. This was first advanced by Pliny, 23 to 79 A.D. From the Greeks and Romans to the Arabs may be a far journey, but little was done in the study of the earth until the Arab astronomers of Baghdad, under the patronage of Caliph al-Mamun, made a series of measurements of a meridian of the earth, which agreed with those of Ptolemy. These measurements virtually sufficed until Willebrord Snell, 1591 to 1626, a Dutch mathematician who had discovered the law of the refraction of light, made a series of measurements of the earth's surface from which he computed the length of a degree of a meridian to be about 67 miles, an estimate subsequently corrected to about 69 miles by one of his pupils, and differing but a few hundred feet from the value now accepted. A measurement by Richard Norwood, circa 1590 to 1675, of the distance from London to York, made in 1636, enabled a degree of latitude to be obtained with an error of less than half a mile, and finally Picard, in 1671, made a measurement of this quantity, which we have seen was sufficiently accurate to be used by Newton in computing the mass and motion of the earth and in demonstrating his law of gravitation. This outline shows that the spherical shape of the earth was constantly held in mind by scientists for about 2,500 years. Other views of the earth's shape also obtained. The idea of a flat earth had to be vigorously opposed by arguments founded on experiment, observation, and discovery. After the phenomenon of a disappearing ship, one of the most important of the arguments against the flatness of the earth's surface was based on the different elevations of the pole star in the sky, depending upon the position of the observer. Now, the pole star and the surrounding stars, though they may be at different heights in the sky, form the same pattern wherever on the earth's surface they are seen, thus showing that they are immensely distant and that lines from all points of the earth's surface directed to the pole star would be parallel or have the same direction. As one travels north, it is seen that the pole star sinks lower and lower in the heavens, or has a greater angular distance from our zenith. If the earth were flat, this would not be the case, for an angular distance of 7.5 degrees difference in the position of two stations 520 miles apart in a north and south line would mean that the star is only 3,450 miles distant, which is manifestly impossible. Furthermore, it is a well-known experience that in crossing the Atlantic from England to the United States, the sun by a watch rises an hour later for every 600 miles we travel west. If the earth were flat, the sun would rise at the same instant over its entire surface. To answer both these conditions, namely the sinking in the heavens of the pole star and the equal delays in the time of sunrise in traveling equal distances, a round globe is required. Still, the globular form of the earth was not accepted generally until after the historic voyage of Christopher Columbus and that epoch of exploration and discovery which resulted in the circumnavigation of the earth in 1519. After the demonstration of the sphericity of the earth came the determination of its exact figure by the systematic measuring of arcs of meridians. When the results were mathematically examined, the conclusion was reached that the earth was not a perfect sphere, but flattened at the ends, or in other words, that it was an oblate spheroid. Newton, in his Principia, published in 1687, showed from theoretical considerations that the earth bulged out at the equatorial regions. On the other hand, in the following century, in 1745, the Cassinis, who were leading astronomers of France and deeply interested in the measurement of the earth's surface, maintained that the earth was contracted at the equator and bulged at the poles, or in other words, was prolate. The difference in the two ideas being concisely expressed by Professor Moulton, who likens Newton's idea of the earth's figure to an orange and that of the Cassinis to a lemon. It is interesting that Newton's proof of the oblateness of the Earth anticipated the direct observations of the astronomer and geodesist. Today, it can be demonstrated in simple form by means of observations of the time of vibration of a pendulum, such as are carried on systematically by such scientific agencies as the United States Coast and Geodetic Survey. It is possible to supply various mathematical proofs of the oblateness of the Earth in connection with its motions and with its relations to the Moon and to the solar system. But these hardly concern us in the present pages, and we may dismiss the matter with the assertion that the ellipticity of the Earth, as determined by Harkness in 1891, amounts to 1/300th as compared with a value of 1/295th established in 1866 by Colonel Clark of the English Ordnance Survey and accepted for many years as a standard, and 1/230th as was given by Newton for the ellipticity of a meridian section of this oblate spheroid. Clark's spheroid of 1866, which is generally adopted in geodetic and other computations, would give a radius at the equator of 3,963.307 miles and 3,949.871 miles at the poles, these figures having been slightly corrected in 1878 in the second place of decimals. The radius of the Earth is in many ways a fundamental measure, especially in astronomy, and for that reason its determination is a matter of no small importance. Thus, observations made with a view of finding the distance of the Moon when discussed and reduced simply give us this distance in terms of the equatorial radius of the Earth, so that to determine the distance in miles we must know the number of miles in the Earth's radius. As a consequence of the spheroidal shape of the Earth, a degree of latitude as well as of longitude varies with the point at which it is measured. Thus, at the equator, 1 degree of latitude is equal to 68.704 miles, but at the pole, a similar degree is equal to 69.407 miles. The difference in a degree measured on the parallels of latitude, which are small circles, is of course obvious, and while at the equator a degree of longitude amounts to 69.652 miles, at latitude 40 degrees, or approximately that of New York, 40 degrees 43 minutes, it would equal 53.431 miles, and at the North Pole it would decrease, of course, to 0. Newton, in his researches on gravitation, by comparing the attraction exerted by the Earth with that of the Sun and other bodies, was able to connect its mass with that of the planets and Sun. The problem of determining the mass of the whole Earth in terms of a given terrestrial body, that is, in tons, pounds, or kilograms,